Hi, my name is Vasco Patricio, and welcome to Data Governance for AI Training Data. It's no question that AI is taking over the world with the explosion of generative AI, for example. And at the same time, disciplines like data governance and data management have evolved over the years, but there's still a lot of misconceptions and confusion about what is data governance, data management, data stewardship, and so on. So I decided to tackle these two topics in this course, where the goal is to teach you how to acquire and maintain high-quality data to properly train AI models. We are going to have modules in this course about a couple of topics, for example, how to acquire data of high quality, how to tag them with metadata, caption them for training, and so on, how to deal with data quality issues in terms of the data actually having low quality in terms of the key features for training, for example, how to de-bias data using, for example, data profiling and data remediation activities when you have uneven distributions of feature values for specific features, but also privacy and security. That is how to apply physical and logical security controls, how to de-identify personal data, and more. At the end of the day, the goal again is for you to acquire and maintain high quality data to train models that are of high quality and are not biased. If these topics seem interesting, I invite you to take a look at the full course. Thank you for watching. Welcome to the Fundamentals module. In this upcoming module, we are going to talk about the building blocks of AI and data. For people who are already familiar with these two disciplines, it can just be a good set of recap lessons. Let's take a look at the content in this upcoming module. Welcome to this Fundamentals module. In this module, our goal is to cover the building blocks of training AIs, data, and more. In this module, we are going to focus on topics such as, for example, the basics of how AI models are trained and the role of training data within those operations, as well as how it changes outputs and maybe introduces biases to the equation, or the usual characteristics of data, the key data disciplines like the M or the G, and how these relate to training data for AI models. That is, the consequences of the different types of data in the actual AI training process. Or for example, the usual data life cycle or common data operations and the specific life cycle stages and operations for training data in specific. We have stages such as curating the data, labeling the data, storing the data, disposing of them, as well as specific stages for when we're talking about training data. For this purpose, we are going to cover 3 specific lessons in this module. The first lesson is called Fundamentals of AI Training, and unsurprisingly, it's about AI training. It's about how the actual training process works, or a general overview of the different types of AI models that we have, the role of training data and how it changes the training process and the outputs of the model, as well as the common challenges that we may face, including biases, data privacy and security, and more. Then, our second lesson will be about the fundamentals of data themselves. Here, we are going to cover the main types of data, and specifically applying this to training data, as well as the main data disciplines like data management, data governance, data stewardship, and so on, and the main definitions that we have to be aware of, such as data quality and others. And finally, our third lesson will be about the fundamentals of data operations themselves. That is, the common data lifecycle stages and the common operations that we actually perform on data, how data are curated, how they are disposed of, and specifically the stages of this for training data for AI models. So as you see, this is a module about the basics of data, the basics of data operations, and the basics of AI, to have a foundation before we dive into more advanced topics. Let's talk about the fundamentals of AI training. We're just going to recap some basics about what AI models are, how the training process occurs, and what is the role of data in this actual training process. It's important to know this because if we want to talk about how data affects AI training, we have to know what is data and what is AI training in more detail. Let's take a look at the basics of AI training. Welcome to this lesson on the fundamentals of AI training. Let's start by covering a basic definition before anything else, which is, what is AI training? Well, training an AI model, put simply, consists of training that model to perform a specific task, either from scratch or fine-tuning an existing model. That is, we are exposing it to a dataset or various datasets, and it's going to learn the necessary characteristics or features of those data in order to replicate them when performing a specific task. or a general task. It doesn't need to be a specific one. Now, there are various dichotomies or various spectrums to AI models. They can be more of one thing or another according to multiple features, which can be, for example, they can be more explainable or more accurate. This is a trade-off. And this means, do we want a model that is more efficient, even if we can't explain the results that well, or do we want a model that really explains its results, even if the results are not that good themselves? This is always a trade-off, and we always have to select a model that is either more explainable or more efficient. We do have other ways to introduce explainability into the equation, but for now, a model can either be more focused on explaining the outputs or actually generating high-quality outputs. Then, is that model generative or discriminative? Generative AI has become very popular in recent years, and it is about generating new data based on the data that we already know, generating images from images, and so on. While discriminative models are everything else, they classify existing data, or at least they draw conclusions based on existing data. So a model can either be generative or discriminative. Then, the model can be static or dynamic. That is, do we have a model that is trained once and just remains like that for the rest of its life, which is static, or do we have a model that is constantly fine-tuned as time goes by? For example, if we have a fraud detection model, as fraudsters come up with new ways to commit fraud, we probably need to update the model to reflect those changes, which would be a dynamic model that is constantly fine-tuned based on new data. Then, is the model trained in a supervised or unsupervised manner? And this simply means, are the training data labeled? So do we caption the data with the features that we want, which is supervised training, or do we let the model learn from the data without any captions at all, and let the model figure it out by itself? Or, for example, is the model a generalist model or a specialist model? That is, are we training a model that can perform a broad set of diverse tasks or a specific model for a niche task? If we have a fraud classification model that wants to detect all types of fraud in the world, that's a generalist model. But if we have a specific store and we train a model to detect, for example, fraud in jewelry transactions of registered users with specific values, that's a specialist model. And actually, these are just some of the spectrums or dichotomies. There are many other possible characteristics of AI models, but these are some of the main ones. Then, another thing which is important to cover is what is the role of training data in a model? This is important because training data are at the core of a model and they greatly define the outputs that we obtain. And it's important to note that I don't just mean whether the outputs are good or bad, which I put in quotes because you never really know what is a good output or bad output, but they do influence them. But it's also, besides that, the characteristics of the output. Are they biased? Are they generalist? Are they specialist? And many other characteristics. So for example, training data can affect the model in the following ways. Not just in these ways, but at least in these ways. First, training data can change how quickly and how well a model learns certain tasks. Based on the distribution of data across different features or different dimensions, the model is going to learn certain things faster than others. Or training data can also cause biases in the inner workings of a model. If, for example, we don't have data on a specific type of subject, then they're not going to be reflected at all in the outputs. If we're training a credit scoring model, and we just train it on people with very high income, and we don't have any data on people with low income, naturally the model is not going to be able to make any predictions related to low-income people. Or training data can also influence the model's adaptability to other tasks. In other words, if the training data only contain information on very specific tasks, that's everything that the model is able to do. It won't be able to generalize. But if the dataset is diverse and broad, it's going to be able to do various tasks related to that dataset. The model can be what we call overfit, just doing a specific set of tasks, or underfit, where it's too generic and it can't even do anything properly. The data can also affect the model's resilience to changes and to attacks. What I mean by this is the following. If we don't train on noisy data or varied data, then the model is going to learn how to produce outputs for a very specific type of data. But once you introduce a version of those data that is slightly different, it's going to go haywire because it doesn't know what to do with them. So it's very important to introduce data that are diverse in different ways so that the model is resilient. It doesn't have any type of input that it doesn't know. And because of that, it can survive different inputs without producing crazy outputs. And for example, the training data can also influence the scalability of the model to new applications. For example, if you train a model that is diverse and broad, and you use it for a specific use case, but you also have information on other use cases, it can easily scale to the other ones. But if you don't, it's not going to scale. In our example, if you train a credit scoring model just on credit scores from people with very high incomes, it's not going to be able to scale to people with low value incomes. But if you train a model on people with all types of income, even if you just use it for high income people, then you are going to be able to scale that model to low income people as well, because the training data contain that scenario as well. So let's crystallize this with an example. We have the Celeb A dataset, which is a dataset of thousands of images of different celebrities, and we can use it to fine-tune a generative AI model to generate pictures of celebrities or pictures of people that look like celebrities. And this can be a generative adversarial network or a diffuser model. The specific architecture doesn't matter here. So in terms of the points that we mentioned, for example, this dataset is going to allow the model to learn a wide array of facial features and expressions, but only those which are similar to the celebrity's features. If the specific dataset, for example, only contains pictures of white men celebrities such as Brad Pitt or George Clooney, you are going to be able to generate pictures of men that look exactly like them, but not pictures of women, not pictures of celebrities or people that look like celebrities of different ethnicities at all. So the variety of features that already exists in that dataset is going to determine the variety of features that you can produce and the images that you output with that model. Then the model is also going to reflect the biases that exist in the dataset. For example, if we have that specific celebrity dataset, do we only have mostly Caucasian or Black celebrities, or do we have celebrities of other ethnicities? Do we have people who are just adults, or also elders and children as well? Do we just have people who are very good looking, or do we have other people as well? Based on the limitations that the dataset has, the model is going to produce outputs with similar limitations. But it's not just in terms of whether the dataset has them or not, it's also about the ratio or the bias. If you have a model that is 75% white people and 25% black people, then there's going to be a presence in terms of black people, but it's not going to be very accentuated. So it's very important to debias the dataset so that all different categories are equal and have equal representation in that dataset. Then, this model can easily adapt to generating new faces, but only if the dataset is diverse enough. Otherwise, it's just going to generate similar faces to the ones that already exist. If we have, for example, a new beauty standard in terms of faces, and those faces are not reflected in the celebrities that already exist, so they're people that have very different eyes or very different cheekbones and so on, then your model is not going to be able to replicate them because the celebrities that you have in that dataset don't have those features. But on the other hand, if those new beauty standards are similar to the celebrities that we already have, then the model can easily replicate those patterns because they already are in the data. And then this model may be resilient to changes in demand, but only if the new beauty standards are similar to the current celebrity faces, similar to what we mentioned previously. So here we're talking in terms of data drift, right? If in the future we have new beauty standards in terms of men or women, and the facial traits are very similar to the ones that we already have in these celebrities, then it's going to be okay. The model can still generate pictures with those traits. But if the new beauty standards are very different from the ones that we have, then we don't have that representation in the data, and the model will not scale to that new use case, if you will. And finally, the model may also scale for other uses if it's trained on other styles. If we want to generate anime pictures, for example, we're not going to be able to do that if the celebrity picture dataset only contains photographs. But if it contains fan art or representations of these celebrities in manga or anime, then we would be able to generate anime pictures. It's all about whether the new use case is reflected in the data that we already have. And the same also goes for types of photography. For example, if we only have pictures of celebrities in very professional settings with high-resolution cameras, we are not going to be able to generate casual pictures as if they were shot from an iPhone or casual phone in everyday life, because we don't have that type of photograph in the training dataset. So as we see, when we are training a model which can have various characteristics, data can have a very significant role because they affect not just the quality of the outputs, but many other elements such as biases, skew, and more. Let's talk about some fundamentals of data. It's important to recap or to learn, if you don't know them, some elements about data. What are the major data types? What are the major data disciplines? And other important miscellaneous definitions, such as data quality, for example. Let's take a look at all of these. Hi, and welcome to this lesson on the fundamentals of data. The first thing that we should cover related to data are the major data types. When dealing with data, we usually have 4 major data types, and they take on unique roles when we're talking about training data. These are master data, transactional data, reference data, and metadata. Let's take a look. So first, we have master data. And master data are usually key entities such as a client, a patient, an artist, if we're talking about an image data set of drawings or paintings, for example, or an author when we're talking about texts, and so on. Usually, you are going to have transactional data in large volume, which represent transactions, and they're associated with an instance of master data, such as a number of transactions for a given client, a number of appointments for a given patient, a number of texts for a given author, and so on. Then we have transactional data, and transactional data usually exist in a large volume in a given database or repository, and they mean actions. They're, for example, financial transactions, such as purchases, but not only. They can be, for example, the works of an artist, if you have a data set of images, or they can even be actions in general, many times in a social media platform, for example, if you're recording logins, registrations, actions such as likes, comments, and so on. All of these are transactions. In certain ways, I even think that transactional data should be called action data. They're just actions in large volume. Then we have reference data. And reference data are very simple. They're usually data that reference something else that gives them meaning. They're usually lists, they're codes, they're flags, or references to other data. Let me give you an example. If you have a list of the 195 countries in the world, and you have a field in the database that tells you, for example, a user's country, it's likely that you're not going to have a character field with the whole name of the country. You may have a field that is a number with a value between 0 and 194, for example. And then you have an enumeration somewhere that tells you number 0 is the United States, number 1 is another country, and so on. So these are reference data. They give meaning to other codes or fields that do not otherwise have a meaning without these references. And finally, we have metadata. Metadata can be thought of as data about data, as the saying goes. So they can be, for example, captions in training data. They can be data quality rules as well, that is, explanations of what is necessary for data to be of high data quality. They can be the definitions. For example, what is revenue in a given revenue field, and much more. Now, it's important to note that each of these four types has a unique role when we're training AI models. The most important ones are transactional data and metadata, but let's take a look at all of these. So first, when we have master data, these are usually what help complement the transactional data. For example, if you're training AI, for example, for fraud prevention, and most of the data in the dataset are transactional data about transactions, literal financial transactions, the master data are still important because the master data may be, for example, the customer who made the purchase. And you can use the master data to obtain information from the customer and add it to a given transaction. So we pull information via a foreign key, for example. So they're useful to complement transactional data. Then we have transactional data, which are usually going to be most of the data in an actual data set for an AI model's training. For example, a large list of purchases, a large list of images, of audio clips, of texts, or others. It's usually a list of actions or a list of properties that you are going to use to actually train the model, usually because they have features that are going to be learned in some way or another. Then we have reference data. And just like with master data, these help complement and give information to transactional data. In specific, in many cases, they can help standardize the values and the ranges for specific fields. In the example that I gave you, you may have countries which are a number from 0 to 194 in one dataset, but you may have another dataset where you actually have the names of the countries as characters. So what you have to do is you have to standardize those two fields. So reference data helps you standardize these values in the transactional data that you are going to use to train the AI model. And finally, we have metadata, the second star of the show in training AI models. What happens here is, metadata is going to be very relevant, usually because of captions. If you are training a supervised model, naturally, captions are going to be crucial, because they define the features that we learn or ignore and how. For example, if you have a dataset of portraits, if you don't label things such as the lighting or the position of the face or the expression of the subject, the AI is never going to really know that it's supposed to learn that. So it may learn irrelevant things like the background or the skin color of the person or the hairstyle or other things which may not be relevant at all. Or they may be relevant, but the only way to know is they have captions that define these features. Then, it's also important to cover a couple of key definitions related to the data that we use. The first is very simple. Data quality, or DQ, the holy grail in data disciplines. Data quality is the name given to the set of conditions that data must have in order to be useful. And data quality may change based on the context. To give you an example, if you have a list of purchases, well, each purchase probably needs to have a price field that has a value in order to be considered of high quality, because otherwise they're not really useful as purchases. But again, it depends on the purpose. You may have a different purpose, such as, for example, preparing your website for high user loads. And in that case, you only care about the number of transactions and number of users from a given country. So the price is not relevant to that context. And in that sense, data quality would not depend on that price being filled for that context. So data quality depends on the purpose for those data. Then, related to this, we have data validity rules. And data validity rules are just the way that you enforce quality. So in our example, if every transaction needs to have a price field that has a value, how do you translate that principle to an actual database rule or any other type of specific direction to force data to be of high quality? At a certain point, there has to be a rule that says every instance of the transaction table or entity, if you're using a different data structure, needs to have a corresponding price that is filled. So these enforce data quality in a practical manner. And finally, it's also important to talk about data definitions. That is, the definition of what each property actually means. For example, what is a price in a transaction? In our example, is it the actual price that the person paid, or is it the price that is listed on the website? If there is a discount or it changes seasonally, is it reflective in the field, or is that reflective in another place? You can have any of these options. You just need to write down somewhere in a repository in a very explicit manner, this is what this field means. Usually in the metadata repository. But at the end of the day, this is crucial because if you have multiple data sets and you want to use all of these and merge them, if the price means one thing in one data set and it means another thing in another data set, there's going to be trouble for sure. Then it's important to just cover very quickly the different data disciplines that we have. First, we have data management, or DM. This is a kind of reactive discipline that aims to directly fix the data. You start projects to remedy data. For example, if you have a list of transactions that don't have a price, you may start a data management project to fill the missing price, either by estimation or by trying to find information in another repository or asking someone who was there at the time, and so on. So usually it's by entering data or trying to estimate the data in some way. It's reactive. It's taking care of data that have low quality. Then we have data governance, or DG, what we're focusing on in this course. And this is a proactive approach that sets the policies and the rules so that data never even enter the organization with low quality in the first place. It's the opposite. So data governance would create policies for new applications or interfaces that say a new transaction cannot even be entered in the first place if the price field is missing. That's the difference, by the way, between DM and DG. DM tries to fix the data after they have already been entered and they are of low quality, while DG prevents low quality data from even entering the organization in the first place. And then we have data stewardship. And data stewardship is nothing more than making the bridge between data governance and reality. Specific teams, departments, applications, and so on. Because if you think about it, it's very easy for me to say every transaction needs to have an associated price. But if we have 12 different applications within the organization or repositories, how are we going to take that general policy and just translate it and cascade it down to the finest level of detail within each app? Usually, you have a data steward within each team or each app or each department that translates the general data governance rules into specific actionable rules. So they convert a general rule into, for example, this specific application can only accept this input if this other input is valid, and so on. And usually, they also take note of specific definitions or rules for a specific team or department. Because as we mentioned, certain departments may use the same word for different things: profit, revenue, sales, contract, and so on. Neither of these is wrong. You can use any of these, but you have to note it down. And usually, the data steward is who does this. So as you see, these are some basic definitions related to data. For example, what are the major data types in the context of AI training? What do the major data disciplines do? And so on. Let's talk about some fundamentals of data operations. That is, data usually have a specific life cycle, and they go through a couple of specific stages. And in AI training, we have specific operations that occur at those stages. So it's important to just be aware of what happens in general to AI training data. Let's take a look. Welcome to this lesson on the fundamentals of data operations. The first thing to cover is the data life cycle. That is, the data in your organization usually go through a couple of stages. They are ingested in some way, or they may be created. They may be pre-processed, they are stored, they are used in some way, then they may be archived, and they may be deleted at the end of the day. So let's talk a little bit about these stages that data go through. So first of all, the data are created or collected. That is, you obtain the data in some way. Maybe you buy it, maybe you scrape it legally, maybe you curate it, or you obtain the data in some way. Then we may have data storage and management. That is, once the data have been created, they have to be stored somewhere. In a database, in a local repository, they enter the organization officially. Then we may have data cleaning and improvement. That is, the data may not have enough data quality when they enter the organization. For example, if you buy them from a supplier and they're low quality data, somebody has to go in and kind of fix the quality of the data. Maybe adding information that is missing, or maybe standardizing some values. So a type of pre-processing before officially using them. Then we have data processing or utilization. That is, you actually use the data. You may use them in reports. You may consume them to train something, like an AI model. You may use them to include in documents, charts, view them directly by users, or any other type. You just use the data at the end of the day. Then, these data may be archived. That is, when the data are no longer necessary, but you don't want to dispose of them yet, you may move them to another type of repository that you don't need to access so frequently. For example, moving them from an operational database to a data warehouse. And finally, once they're really not necessary anymore, you may dispose of those data. And based on how sensitive the data are, you may need to do it according to a specific method of destruction or a specific time frame. Now, for training data in specific, the same stages apply, but we can include some additional stages or clarifications here. So for example, we start by creating or collecting the data. So far, so good. Then we store and manage the data. Same thing. Then, when we're cleaning and improving the data, we do have some unique operations that may occur here. For example, we may annotate the data. That is, capturing the training data. Just like you would obtain a list of photographs, for example, in a general setting, if you're training an AI model, you would obtain the list of images, you would save them, but then you want to caption them before you train the AI model. Then, when it's actually time to process or utilize the data, we have some unique uses or operations here. The first is, for example, data augmentation, which is creating more synthetic data when your dataset doesn't have enough data. In our example, if we have a list of 20 images, for example, let's say that we actually need 40. We may use certain techniques to create synthetic data. For example, training a very quick AI on those 20 images to produce other images that are kind of similar to these because it's not that well trained, but then selecting the best ones that really look like the source images and then adding those to the dataset. So we are augmenting the dataset with new data that is synthetic or created from nothing. You can even use LLMs in the case of text. For example, feeding an LLM like ChatGPT a list of 20 customers and then generating other 10 realistic seeming customers, which are completely artificial, but that would work for this case. By the way, don't do this, only do it if it's your locally hosted LLM. Don't paste confidential information on ChatGPT, please. Then, another unique activity to training AI models is feature engineering. That is, selecting the features that we want and captioning them. In our example, if we're downloading a list of portraits, for example, to train an image AI, we have to select which features are going to matter. For example, the position of the face, the facial features, and so on. Because we may have other features of the data that don't really matter to us, such as the background or the lighting, or these may actually matter depending on the type of AI model that you're training. But at the end of the day, you have to select what are the components of the data that we want to focus on and manually caption these. If we're talking about supervised or semi-supervised learning, naturally. Otherwise, we just skip this step. And then, we may also have dataset splitting and model training. What happens is, if you have a list of, for example, 60 elements in a dataset, you're not going to use all 60 for training. You're going to create a training dataset, a validation dataset, and maybe a test dataset as well. And in certain models, such as generative AI models, you have specific types of training, such as, for example, regularization images, which regularize the loss function, and they're used to obtain more specific details, such as to train on a person's face, for example, to learn the facial features. But at the end of the day, you're usually going to split your dataset because you're not just going to have one unique dataset. You're going to split it for different purposes, and you're actually going to train the model at the end of the day. And then we usually have data archiving and data disposal as usual. Once the model is trained, if it has only been trained once and you're not going to need the dataset anymore, you may archive it or you may get rid of it entirely based on what you need. It's also important to clarify that based on the type of AI model that we're dealing with and the dataset, we may need to prepare the data or pre-process them with a range of different techniques that can be used here. For example, one of them is cleaning and standardization. As we mentioned, taking data that may be in various formats, such as countries, addresses, phone numbers, and so on that may exist in different formats in different datasets and just harmonizing it all. Or for example, normalization. Related to the previous point, as we mentioned, you're pretty much taking different values that have to do with specific numbers, and they may have different ranges. For example, you may have a range that is considered in absolute units, such as temperature, in one dataset, and in the other one, it's considered a percentage of that range. So you need to convert them all to the same range of numbers so that you can merge the dataset at the end of the day, or just understand it. Then we have annotation and captioning. Super important, especially for supervised algorithms. You have to caption the data, and you have to caption them according to the features that you want to learn. Then, data profiling. This is important because certain datasets may be imbalanced, and you need to do data profiling to figure out if the dataset is skewed or biased towards any type of feature. For example, if you have fraud transaction data to train a fraud detection AI, is it possible that you're only dealing with fraud of low volume purchases or low value purchases? For example, if you have a list of transactions for a fraud detection AI, it's very possible that 90% of transactions are low value transactions and not high value. What is the only way for you to know? To do data profiling according to the value of the transaction. And this can occur for any type of dataset for any type of use. For example, facial features of specific ethnicities while others are underrepresented in image AIs. Or for example, in text AIs, having a lot of text that has a very specific tone or a very specific type of language and not other types of language, right? And then you end up with an AI model that is biased and you wonder why. You have to do the profiling. And then feature engineering. As we mentioned, you have to caption the data, but you also have to select within the dataset what are the features or the properties that matter to us and caption according to those. Because otherwise the model is going to learn all of the features at once, including the ones that don't matter to you. It may become confused, outputs may become irregular, or it may not learn anything at the end of the day. So as you see, we have a certain data lifecycle and specific operations that apply to AI training data and specific preparation techniques for these types of data. We are now at the end of the Fundamentals module where we covered some basics of AI training and data. Let's recap the lessons that we've covered and some key takeaways for this module. Welcome to this lesson on concluding our first module about the fundamentals. In this module, we focused on the fundamentals of data and of AI training. In specific, we touched on topics such as the basics of how AI models are trained and the role of training data in this process, especially with captions for supervised learning, but also even in terms of how the different characteristics of data actually affect the model, the biases, the quality of the outputs, and a lot more. Then, we touched a little bit on the usual characteristics of data, the main data types, the main data disciplines, and their consequences and importance to AI training. Then, we talked about data operations, the usual data lifecycle, including operations specific for training data, the common data operations, and the specific operations that we also have in terms of pre-processing or preparing training data in specific. What are some of the most important key takeaways from this module? Well, training data influence model behavior, and not just in terms of the outputs, but biases, adaptability to tasks, whether data drift is going to affect them, adversarial robustness, and a lot more. Then, the main types of data are master data, transactional data, reference data, and metadata. Out of these two, the two types that most matter to training AI models are transactional data, because they are in high volume and most datasets are comprised of them, and metadata, because they contain the captions to train models in terms of supervised learning. Then, data quality simply means that data are of high quality according to a specific purpose that we have in mind. We may have specific data validity rules which enforce this data quality, and the definitions of the specific terms are also crucial. When we have low data quality, either data management aims to fix it, or data governance installs a new policy to prevent low data quality in the future. Then, the data lifecycle has multiple stages. Data are created or collected at some point, they may be pre-processed, they're stored, they may be used, archived, and disposed of. And for training data in specific, we have a couple of additional stages. We may have some additional cleaning and standardization to make sure the dataset is of high quality, and we may have additional operations such as splitting the datasets for different purposes, feature engineering, and training the model at the end of the day. And finally, some common operations that we may perform on training data include these: cleaning and standardization to make sure that different datasets can merge well into one unified dataset for training. We may normalize different values, especially if they have the same meaning but they reference different systems. Maybe one system is relative in terms of numbers, maybe the other has absolute values, but we have to convert them all to the same standardized format. We may annotate the data in terms of the captions and specifically for the features that we wish. And for that, we also have to do feature engineering, which is selecting the features of data that we most care about and possibly other operations, splitting the datasets, training the model, and more. And with this, we close the fundamentals module, where our goal was to cover the basics of AI training and data. We are now at the data sourcing and curation module, where we are going to cover some lessons related to how we collect datasets, how we integrate them, and what happens to them. Let's take a look. Welcome to this intro to the second module, which is about data sourcing and curation. That is, how to actually acquire our datasets and take care of them. What are some of the topics that we are going to cover in this module? Well, we're going to cover where datasets can be curated from and the consequences of various sources and dataset specifics. That is, different data sources may have different levels of data quality or introduce biases of different types, for example. Then, how different datasets can be reconciled and integrated and what to focus on in this process. That is, they may have the same properties with different values or different ranges, they may have completely different properties, they may have properties that are represented as different features, and so on. Also, why captions matter and why they matter a lot during the curation process of datasets, and specific examples of these for different types of datasets, image, text, and structured data, as well as the different methodologies to captioning, such as automated, manual, or a hybrid of these two. In this module, we have 3 specific lessons. The first is about data curation. That is, where do we actually obtain the data from and the different challenges that we may face with different datasets, whether they are acquired, bought, or come from different sources, and the different characteristics that they may have based on those sources. Then, our second lesson is about dataset integration. That is, you've curated multiple datasets. Now, how do you integrate them to obtain the final dataset in a way in order to be actually able to train an AI, with a focus on data stewardship so that you can properly label and annotate your data to know what you have so that you can properly merge them to obtain that final dataset. And then we'll have a lesson specifically about captioning and formatting. That is, why captions matter for the different types of datasets and what features you usually caption, as well as the process that you usually follow to actually caption those datasets. As you see, this module is all about creating datasets. Where do we get the data from, and how do we reconcile them? Let's talk a little bit about data curation. We may obtain data from multiple sources, and this is important because those different sources give data different characteristics. Let's take a look. Welcome to this lesson on data curation, where we are going to focus on how to actually obtain the data for datasets. When we're training an AI model, the data can come from anywhere, really. Because of this, it's important just to cover an overview of these data sources and what may vary among them. First, we can have internal datasets. That is, we compile, for example, a list of internal transactions to train a fraud prevention engine. If you're an artist, you curate a list of your artworks in order to train a generative image AI with your own style, and so on. Internal data. Then, we can also purchase data or obtain them from partners. For example, you may buy a list of royalty-free drawings to train an AI model on that artist style, if they're willing to sell those or license those. Or you can usually obtain data from different sources if you have partners who are willing to license those data. Then, you can also use openly sourced data from public websites, from NGOs, from governments, from competitions, such as, for example, hackathons, crowdsourced data, open data, or even scrap data if the source allows it in an ethical manner. That's another source that you can use. And then we can have synthetic data, and these are data that you create yourself. For example, based on a list of existing transactions, which may be a good list, but you may not have enough transactions, you may create synthetic transactions based on those. That is, you create artificial transactions with similar characteristics, but that don't really exist. In the eyes of the model, for the purpose of training, they're exactly the same, they have similar features, but you know that they're not actually real. Then, data consistency also matters, because naturally, since data can come from multiple sources, and varied sources at that, we may face inconsistencies in various properties. For example, in terms of the formats. That is, you may have multiple datasets where the quality level is the same, but the actual values are different. For example, you may have a dataset that has the dates as year, month, day, and another dataset that has the dates as year, day, month, for example. And you need to harmonize this before merging the dataset, naturally. Then, the sampling itself also matters. That is, let's say that you have a dataset of credit scores, or 2 datasets in this case. Maybe one of those datasets has credit scores that were estimated by hand 10 years ago, And another one has credit scores that are estimated by machine learning with 90 different criteria. The scores are all from 0 to 100, but the way that you calculated them is very different. Then, the data quality level itself may also vary across these datasets. For example, if a price in a transaction is an essential feature, you may have a dataset with transactions that have prices and another dataset of transactions that don't have prices. And this one is a bit more serious because in this case, it's harder to fix. Then, the source trustworthiness may also change as well. For example, you may have two datasets of academic articles, but one of them comes from a top-tier university and the other dataset comes from a lesser-known university. So for example, if you're training a text AI on academic articles, you can really trust the articles from one dataset, but you can't trust that much the articles from the other dataset, and this becomes a problem. And finally, the data themselves may vary. That is, for example, you may have two datasets with credit scores that include similar subjects, but the data are different. That is, the datasets are contradicting each other. You may have credit scores that rely on different criteria, so they were used for the same population, for example, the same exact people, but one of them has a set of scores and the other one has another set of scores. If the features that are contradictory are numerical, you can just average them out, but if they're not, then we have a bigger problem. So as we see, datasets can come from multiple sources, and this is important because they give them different characteristics, and we must take this into account when training with those data. Let's talk a little bit about dataset integration in general. If you have curated multiple datasets, how do we reconcile them? Usually, we have to define what are the key features that we need to find across all datasets, and we also need to harmonize those datasets. And data stewardship plays a big role in this type of operation. Let's take a look. Welcome to this lesson on dataset integration. Let's say that we've curated multiple datasets and now we need to harmonize them, and we need to aggregate the main dataset, the final one, that we're going to use for model training. Usually, we have to focus on two distinct things here, which are crucial for this process. The first is defining the key features to be learned. And this is important because this dictates which datasets are of quality and which aren't. For example, if you want to train an image AI for studio photography, then the lighting is a crucial feature. If one dataset has the lighting tagged and the other one doesn't, then you can't harmonize them yet. So datasets that actually have this feature are of high data quality, and datasets that don't have it are of low data quality. For example, if you have a whole dataset where the lighting is the same, you're not really going to learn anything because there's no variation in the feature. So that's low data quality. So you can't merge the datasets until all of them have high data quality. Again, if you're training the image AI for studio photography and you have a dataset of 100 pictures with various types of lighting, and you have another dataset of 100 pictures where the lighting is all the same, one of these datasets is pretty much useless. Or it's not useless, you can learn that specific type of lighting, but you're not going to learn much. Then, the second thing that we must focus on is on harmonizing the different datasets. That is, we may have datasets, as we mentioned, that calculate the same things but with different ranges or even contradictory values. For example, credit scores. If one of the datasets has a credit score as a qualitative measure, such as good, very good, or bad, very bad, and the other has the credit scores as a quantitative measure from 0 to 100, for example, you're not going to be able to merge those datasets until all of them have the same feature in the same language, if you will, until the ranges are standardized. One way or another, these datasets have to be harmonized. They have to talk about the same things in the same language, if you will. The features must have value ranges that correspond to each other, because otherwise you cannot even establish a correspondence between the datasets. Now, this is an interesting operation because the role of data stewardship here is very relevant. Data stewardship plays a crucial role because it translates the data governance policies into specific elements. They help define, for example, the required features. That is, within an organization, who is going to define what are the essential features for training? Usually, data stewardship is going to record those definitions. It may be together with an AI expert that is focused on the training method and that knows this, but the data steward has to focus on this. So for example, the data steward works with the business users to reverse engineer, based on the results that you want, the essential features. In our example, if we want an image AI that can produce studio photography, they're the ones who are going to speak with the business user and think, hey, to obtain studio level photography, what are the features to focus on? Maybe the lighting, maybe the poses of the model, maybe some other things like makeup in the model, and etc. So they reverse engineer the features to be learned, and therefore the features that we need to have in the datasets that we're curating in order for them to be of high quality. And another thing is the metadata of the various sources. That is, in the metadata repository, where data stewards require things like the business definitions, the validity rules, and everything else that is translated from DG locally, they should note down the elements such as the trustworthiness of each dataset, or how that dataset was obtained, or the level of sensitivity of the data and others. Because remember, we have to protect those data and we have to know what we have. If you just collect all of the data in the organization and you put it all in one database, later you're going to ask, hey, where did these specific data sets come from, right? These specific data ranges that have biases. Did they come from a specific source? Did we buy them? Did we curate them? And if you don't record this, you're not going to know what you have. So you want to be a little bit nerdy about it, and you want to know exactly where did these records come from? What is the level of trustworthiness? Do they contain personal data? What are the features that are labeled? And so on. So somebody has to go in and literally annotate all of those properties around the data, which are the metadata, and the data stewards are usually the ones that do this. This helps establish, for example, priorities. If you have conflicts between two conflicting data sets, which one are you going to prioritize? Well, the metadata is going to tell you which ones have a higher level of trustworthiness and quality. And it helps you to later track back biases, for example, to their specific data sets. You're going to be able to know later on, hey, these 20 specific transactions came from a specific data set that we bought from a partner. So maybe we don't want to buy it again, or maybe we want to have higher demands when we buy from them, for example. So as we see, when we're integrating datasets, we have to know what are the key features, and we have to harmonize the datasets in order to create a homogeneous one. And data stewardship really plays a role in helping with this process. Let's talk about captioning and formatting. For supervised learning, it's crucial to caption the features that we need in a dataset. And this is important because they may change. For example, for a dataset of images versus text versus structured data, the captions may be completely different. And the way that you caption the dataset itself may also be different. Let's take a look at all of these elements. Welcome to this lesson on captioning and formatting the datasets that you curate. Captioning and labeling of the data is crucial for supervised learning because you want to label actively the features that you want the model to learn during training. Otherwise, it's not going to know what to learn during training, and either it learns too many things, including unnecessary ones, or it doesn't learn anything because it's underfit. So captions help guide the actual model's training by labeling the features that you want the model to learn. And usually, we do this in the form of captions. For example, if you have a dataset of texts to train a text generative model, you want to caption features such as the tone of each text or each article, the style, whether it's formal or not, the sentiment in the text, the vocabulary used, and so on. When you caption these properties, you help detach from them during training, and the model knows what to learn and not. For example, if you have a set of texts that appeal to emotion, they're very sentimental, they're very polarizing. If you don't label that explicitly in the text, in the captions, these are sentimental or emotional texts, then the model is going to learn that as if it's a default feature. Because if you don't label it as being emotional, then the model is going to think that all text is like that by default. So if you don't caption these features, then the model is going to learn them by default. But when you caption them, the model learns to separate that. So if you label all of these texts, for example, as being emotional, then the model is going to think, oh, these are emotional texts, so I want to extract the emotion from them, and I want to learn what's underlying in that text. And the same for any type of feature. For example, if you have a data set of images to train an image generative model, such as photographs, you want to caption something such as the number of people, the background, the lighting, the poses, the objects which are present, and so on. In our example of the lighting, if all photographs have a very specific type of studio lighting, if you don't label it as studio lighting, then the model is going to think that that lighting is by default. So every image that you generate is going to have studio lighting. But if you caption that as studio lighting, then the model is going to detach that from normal photographs, if you will, and you're going to be able to generate pictures with or without the studio lighting. Or for example, if you have a data set of structured data of client profiles to train a purchase prediction model, then the number of purchases, the demographics, the job title, the monthly recurrent revenue, and so on are all features that you want to be present. Again, the same lesson applies. Every feature that you don't caption actively, The model is going to learn it by default and replicate it in every output because it thinks that it's normal. Or, for example, for a dataset of medical images to train a diagnostic model, you may label features such as the organs or the body parts which are present, or the disease markers, or the evolution stage of that specific condition. That is what identifies those specific unique pictures. Because if you don't label these, again, then the model is going to think that by default, all pictures have a specific type of condition at a specific stage, and so on. And again, it all starts with asking what is relevant for our model. Those are the key features that we want the model to learn during training. Now, how do we actually caption these datasets, right? Usually captioning is done in one of three ways. The first type is automated, and this is a very fast process, but it also has a high level of noise. As the name indicates, we use some type of software to automatically tag the datasets. For example, a batch captioning system for images in a folder, or a batch NLP tagger for text in a dataset, and so on. You don't check it, you just let it run automatically. So sometimes, just like any other type of AI, it may have false positives or false negatives. So it may output the wrong tags for specific datum in a dataset, but you're not going to be able to know that because you're not checking. That's why we have the next stage, the next option, which is semi-automated. And this has average speed, but it has an average level of noise. You have a human that interprets the outputs of the automated tagger and changes something that may be wrong here and there. That's why it's not as fast, but it has a little bit less noise as well. So what you do is you run that same automated software for your specific type of dataset and you review the captions manually. Or alternatively, you can also go about it another way, which is you caption manually, but you caption in groups. For example, you take a group of photos, like 5 or 6 that have the same type of lighting, you put them in a folder, and you run a small script to attribute the same captions to all of these. And you do it in a semi-manual way, right? So you can do it bottom-up or top-down. You can do it automated and review manually, or you can start manually but caption in batches instead of captioning one by one. Either way, it's a little bit better than automated because it has less noise. And then the best way is to do it manually. But as you're probably guessing, it has very low speed and it has a lower level of noise as well. So what you do is you have somebody, which usually needs to be somebody with domain expertise, to manually tag every datum in a dataset. And this is great for small datasets. For big ones, it doesn't scale as well. For example, if you have a transaction dataset to train a fraud prevention AI, then the person who is going to label those transactions must be somebody with financial knowledge, and so on. So as we see, it's important to consider that we have different types of captions for different types of datasets because the key features vary across the different types of media. And it's also important to consider that we have multiple ways of captioning a dataset with different levels of speed and also human interaction. With this, we reach the end of this module on data sourcing and curation. Let's take a look at the lessons that we've covered and cover some key takeaways. And we're now ready to close the second module on data sourcing and data curation. What topics did we focus on in this module? Well, we focused on where datasets can be curated from and the consequences of the various data sources and dataset specifics, whether they have biases, higher or lower trustworthiness, level of quality, and so on. Also, how different datasets are reconciled and integrated, and what to focus on during this process. That is, identifying the key features and making sure they're present, and harmonizing those datasets, speaking the same language among values, and also why captions matter in specific datasets, examples for different types of datasets, as well as what the process actually looks like. What are some key takeaways from this module? Well, there are multiple possible sources for datasets. We can purchase them, we can integrate them, we can obtain open data, and so on. And these may introduce variation in the data formats, in the sampling methods for the same values, in the high level of data quality itself or low level, in the level of trustworthiness, and or the data themselves, because they can be contradictory. Then, datasets are integrated by focusing on the key features that matter to us in terms of learning, and also by harmonizing the different datasets with various data formats, or ranges, or values. All sub-datasets must have values for our key features. That is, they must be of high data quality, and they must also have values in the same formats. Finally, captioning datasets is crucial. Different data formats have different features that require captioning: the tone in text, the lighting in photographs, or any other type of feature that may be important to a specific dataset. But at the end of the day, every dataset has features which are key to learning, which are usually calculated by a business user together with a data steward, reverse engineering the goals to calculate the key features to learn during training. And again, different captioning methods have different speeds. They can be automated, which is fast but has a lot of noise. They can be manual, which is very slow but has a low level of noise, or hybrid, which is somewhere in the middle. And with this, we close this module on data sourcing and curation, where we focused on how to obtain data and prepare them to create data sets. Welcome to this module on data quality enforcement, where we are going to focus on the tasks that allow us to assess and change the level of data quality in a specific data set. Let's take a look at the lessons in this module. Welcome to this third module on data quality enforcement, where we are going to focus on how to identify data quality problems, how to address them, and how it works at scale. In this module, we are going to have topics such as, for example, how data profiling is performed to detect biases or problems that datasets may have, and how data governance influences data profiling, because it's not data governance that actually executes the profiling, but we'll get to that. Or, for example, how cleansing and pre-processing of the data are actually applied to datasets to make them easier to handle and easier to learn features from, reducing noise. Or, for example, how data are actually remediated or fixed, if you will, to remove problems that reduce their quality and to make them more useful for AI training, increasing their data quality. Or finally, how data governance influences data-related operations at scale and the challenges that appear when you have various teams, various models, various datasets, or even various use cases for the same dataset. In this module, we have 4 key lessons. The first lesson is about profiling for data quality. As the name says, what data profiling is, which is analyzing datasets to find data quality issues, how it applies to training data and specific, and the role of data governance in this process. Then, data cleansing and pre-processing, what these operations consist of and how they can be applied to datasets to reduce the noise that they have and to make them more relevant and useful for AI training, including feature engineering, which is changing or adding features that better represent what we want to learn, because the original features of the data may not be enough. Then, our third lesson is about data remediation. This is where we actually get to fixing data that have low data quality, getting in and fixing them. What to do when we have data quality problems, such as missing values or outliers or values that don't make sense, and how we actually remedy those situations. Then, our fourth and final lesson is about data governance at scale, because all of this works locally, but what are the challenges that appear when you have multiple datasets, multiple teams, multiple use cases, and how do we deal with those to make sure that the process doesn't break when it becomes bigger? So as you see, this module is all about data quality in datasets, how to make sure that a dataset has quality, and if it doesn't, how to remediate that. Let's cover data profiling. Data profiling is nothing more than investigating a specific dataset to know what may be wrong with it. And if there's something wrong, then we are going to later remediate it. But it's deeper than it seems. Let's take a look at how data profiling is done. Hello, and welcome to this lesson on data profiling for data quality. First of all, we have to ask, what is data profiling? Data profiling is merely the action of examining a dataset and checking for data that may be missing, that may be biased, in incorrect formats, or others. It's usually performed by data management, but it's according to the rules set by data governance. So data governance influences it indirectly, and data management does it directly. Data profiling contributes to, for example, finding missing values for key features. In our example that we always use, if we have a list of transactions that must have a price value, data profiling is going in and seeing which records don't actually have a value for the price feature. Or for example, finding biases in key features. That is, if ethnicity is a key feature in credit scores to protect against bias, that is making sure that it's varied, and some ethnicities are more present than others, then data profiling goes in and calculates the distribution. Do we have, for example, Caucasian people overrepresented or Indian people or Black people underrepresented? So that we can fix this later by changing the sampling so that all ethnicities are represented at an equal level. Or finding, for example, outliers, such as values that just may be wrong, such as, for example, wrong automated captions when you're captioning the dataset, or, for example, wrong values themselves. Let's say that you have a machine that reads pressure, for example, in a physics project, and some values are 0, but you know that they're not 0. They're undetermined because the machine malfunctioned, but because the field was a number field and you had to input the value, the machine input the value 0. Maybe it's actually a code that must be changed because 0 may mean that the machine malfunctioned. But if you don't know this, then the 0 is going to appear as 0 in terms of pressure, which is not real. So you have to detect the outliers and what these numbers may mean when they don't make sense. Or for example, validating the data integrity itself of the dataset. For example, we may have duplicate images in an image dataset, or we may have duplicate transactions in a financial transaction dataset. If we don't remove these duplicates, they're going to be overrepresented. They're going to be represented twice as much as any other transaction or image. And in some cases, you may actually have parts of a dataset missing. You may have a script, for example, that curates a whole dataset and exports it to a folder to be able to train an AI model, but maybe it didn't export from a specific folder. So if you check the numbers of the datasets, they won't match. So it's about integrity, making sure that all records are there, but only all of the records. Now, when we talk about data profiling, we have to talk about the data dimensions, because data have high quality or low quality according to a specific dimension. Let me clarify. One dimension, for example, is completeness, whether the values are missing or not in an entry. If you have, for example, the transactions that don't have a price, as we mentioned, they don't have low data quality in general. They have low data quality according to the completeness dimension. Or, for example, credit scores that are missing the actual score, and they're going to be useless for training because the values are missing, and they're going to be polluting the dataset because they change the averages or they're interpreted in a different way. Or you may have, for example, the accuracy dimension, which means that a value makes sense or doesn't make sense according to its context, that it's congruent or not. And you can already see here that data may be of high quality according to one dimension and of low quality according to another one. For example, if you have a value that is wrong, the value is there. So that record is of high data quality according to completeness. It is complete, but it's of low data quality according to accuracy. So an example would be just like we mentioned, IoT readings that have 0 as a value when the value should actually exist. And maybe the machine malfunctioned or there's something else going on. Or, for example, uniqueness, whether that value exists only once in the data source. There are no duplicates. For example, if you have photos which are duplicate in a dataset, they would be of low quality according to the unique dimension because they're overrepresented. You have duplicates. Or, for example, timeliness, whether the value is up to date. For example, if you have a list of transactions which are valid but are old transactions, they may be less relevant in today's financial climate, and they may be of low quality in terms of timeliness. For example, if you're using a dataset of purchases from 30 years ago to train a fraud prevention AI, the product values may not be the same, the payment methods may not be the same, the quantity of purchases that somebody does online may not be the same. So they are there, they're complete, they're accurate, and they are unique. They're just not relevant in terms of timeliness. And as we mentioned, an entry may be of high quality according to one dimension and of low quality according to another one. A value may be unique, but it may not be accurate. A value may not be complete, and in that case, it may not be accurate as well, but it may still be unique, right? So when we're doing data profiling, we have to be aware that low data quality and high data quality are according to a specific dimension. And finally, it's important to talk a little bit about the roles of data governance and data management, because data management professionals are usually the ones that actually go in and perform this profiling, and also the remediation later on. But the whole process also involves the G and the S as well. So the process is usually the following. First, we have data governance that defines the general principles from above. So they define, for example, that all photography datasets must be of high quality to train a generative image AI model. Then, data stewardship translates those into local rules for local teams. For example, if you have 30 different apps or 30 different databases, how do you translate those general principles? That's the data stewards for every single team. So they, for example, define that this specific dataset of 50 pictures for this team to train this generative image AI must have tags for features such as lighting, pose, and background. That's the definition of high quality for this dataset for this team. And then data management is the team that goes in and profiles that dataset to check whether they have those features present and remediates them. So for example, they find out that 90% of the pictures are in the same pose, so we must obtain pictures in other poses. And some lighting tags may be wrong, so they're not accurate, so they may create a script to purge those from the sub-datasets. So pretty much, data governance decides, data stewardship adapts, and data management executes. That's a good way to summarize it. So as we see, data profiling is all about finding values that don't make sense in one way or another, depending on the different dimensions, and which mean that the data don't have quality according to that dimension. And it's usually done locally by data management, but according to the principles and rules set forth by data governance. Let's talk about cleansing and preprocessing. This is pretty much an additional optional step that may come before using a dataset. and that may increase the quality of that data set. It may be about standardizing and harmonizing values, but also creating additional features which may be more useful for training than the ones that we originally have. Let's take a look at all of this. Welcome to this lesson on data cleansing and preprocessing. So, cleansing and preprocessing are operations that improve the quality of the data or how easy it is to handle those data in order to better use them later, such as to train a model. Usually, this may be an optional step because you have profiling, and if it detects data quality problems, then you remediate the data. But cleansing and preprocessing may come between the profiling and remediation. It's just making data easier to use. Or some people even consider that the cleansing and preprocessing are part of remediation, because if the data had enough quality, you wouldn't need to do anything to those data. But anyway, we usually have two major groups in terms of cleansing and preprocessing. First, you have cleansing itself. And this consists of reducing noise in the data. For example, correcting errors, reducing noise, or handling incorrect values. It's harmonizing the data in a way. For example, correcting mistakes in text, or the graphical mistakes, or formatting images to the same dimensions in an image dataset, or filling missing values in transactions. And you can see how this kind of crosses the line sometimes between just making data easier to use and actually fixing problems. And then we have data preprocessing. And this consists of streamlining a dataset. As the name says, you're processing something to make them easier to use later. You can normalize and standardize values, or you can engineer features which may be more relevant to us than the existing ones. For example, you can normalize price ranges, you can normalize image color schemes, and so on. They're things that may not be essential, but they're useful to do because they make your life easier later when calculating the features. Or you calculate the features to make life easier later on. And talking about features, by the way, one of the key actions that we can do here, which is optional but highly effective, is feature engineering. That is, the creation of new features or the manipulation of existing features to make them more relevant than the current ones that we actually have. Let me give you a specific example. Let's say that in a transaction dataset, we only have basic properties for features: the price, whether it's fraud or not, the user ID, and others. For example, it could be interesting to create a transaction frequency feature, which is the number of transactions per time frame, or transaction velocity, as we use in the fraud prevention lingo as well. So for each transaction, we now have the associated frequency of the associated client. But we have to run for the whole dataset to calculate that and then embed it in each transaction. This may be interesting because now we know whether this specific transaction looks suspicious compared to the frequency of transactions by that user. It's something that wasn't there originally, but now that it's there, it gives us additional information. It's a little bit like calculating those advanced indicators in terms of the stock market, like the Bollinger Bands for volatility or the price momentum and so on. The basic features are there, but you can use some formulas to calculate more advanced ones which clarify some aspects. Or for example, imagine that in an image dataset we have features such as whether it's an indoors or outdoors photograph and the lighting type. In this case, it could be interesting to create a time of day feature as well. That is, for outdoors pictures, when was the picture taken? Because that way you can detach the artificial lighting from the natural lighting, and you also caption the specific types of natural light, because then you're going to be able to have outputs with specific types of natural light. Again, it's not necessary, but it's very useful. Usually with feature engineering, it's especially useful when the new features are more useful than the current ones. This is a bit obvious. If they weren't more useful, we wouldn't do it. But you know what I mean. We do it to have more advanced features that help us more. And you may ask, what are the actual patterns to create these features? Is there a specific formula or model? Well, one type is creating ratios of existing features. For example, if instead of just having lateness in attendance records, for example, you could have normalized the lateness by the distance of the worker's home from the office. Because maybe somebody that lives around the block and is 5 minutes late is not the same as somebody who is traveling 100 miles per day and is 5 minutes late. You may want that normalization or not at all. It's an option. Or, for example, normalizing a feature value by its average, because this tells you how different it is than the average. For example, how many fraud flags this user has received averaged by the average fraud flags in this location. Because sometimes somebody is shopping in an area that has a lot of fraud. And if somebody is traveling, for example, to that location, they may be flagged as fraud just because they are in that location. But if you average the indicators of fraud in that location by the indicators of fraud of this person in specific, you can be a little bit more lenient. entrenchment, for example, for people who are traveling to those locations. Or for example, creating categories or flags based on existing values. For example, you may bucket a user's age into age groups. Now instead of having probably 60 or 50 different values, now you only have 4 or 5 different ranges, and that's much more useful in order to train a specific model. Or for example, you may create a new property that says past issues. That is true if the person had an issue in the past or not if they haven't. Because for example, in a list of transactions, you may have a list of past issues, which is another database, another table, and you can't embed that information, but you can just create a flag that says, hey, has this user had trouble in the past or not? And if it's true, then it could be another indicator of possible fraud, for example. So you create new features based on specific values. So as we see, cleansing and preprocessing have the goal of making data easier to access, easier to view, and easier to use when training a dataset, which makes them more useful and increases their data quality. Let's talk a little bit about data remediation, and this is usually what people think of when they think of fixing data. It's taking wrong values and either eliminating those records or replacing them with more accurate values or other operations. Let's take a look at this operation. Hi, and welcome to this lesson on data remediation. Data remediation is the step that logically follows data profiling. If we have curated a data source that has data quality issues, then we need to fix it in a way, or remedy that source using the fancy language. This is usually performed by the data management team again in what we call a remediation initiative or project. So right after we curate the data or years later. You may have situations where if the organization is running well in terms of data, you can identify issues immediately one day after you buy a dataset or immediately after you curate it, and the team intervenes immediately. Or you may have organizations where 7 or 8 years afterwards, an executive launches an initiative and they find out that half of the data have problems and then they fix them. So depending on the organization, this can vary a lot. But usually it's the same logic in terms of process. Data governance sets the standards, data stewardship translates them into specific teams and departments, and then data management goes in and identifies those issues and fixes them. And by the way, this can be for a project of any size. You can fix a data set of 10 records, or you can have a master data initiative to completely revamp the master data like customers in a whole organization with millions of records. Data remediation is just the act of fixing data by data management. It can be a lot of data or not, it can be fast or not, it's just fixing data in a way. So it can include specific initiatives such as, first, removing incorrect values. You can have the dataset such as the one with the IoT with the 0 values that we mentioned, where the values are outliers or they're clearly wrong to anybody who reads this, but somebody has to go in and either remove the records or try and guess the actual values. For example, replacing those incorrect values, which is an alternative. In the same example, instead of removing those records with a 0 value, you speak with the domain expert and you try to actually guess what the values would be for those cases. And this depends on the use case, right? Naturally, there are cases where you can estimate the values, it is tolerable, but for other cases, it may not be tolerable. For example, for credit scores, if the credit score is missing, you may not want to guess it because it may not be acceptable, okay? But there may be other use cases where it's completely okay to just guess the values when they're missing. Or for example, consolidating duplicates or contradictory values. That is, reconciling duplicate values or values that contradict themselves for the same entry. In our example, if you have 2 different credit score data sets where one was estimated by hand and the other was calculated by an algorithm for the same exact person, maybe the one calculated by the algorithm takes precedence, or maybe it doesn't. It depends on what you labeled in terms of the trustworthiness of the data, where the data came from, their level of quality, and so on. But either way, the data management team goes in and they're going to replace or remove those values. And finally, they can also enrich information. Even if the data already have a high level of data quality, maybe you can increase it even further. For example, you can add additional data from new sources to improve the entries. If you have a data set of transactions for fraud prevention, maybe if you get data from other merchants, which may not be useful to you, but give you a baseline of fraud in a specific region or for a specific type of product, you can embed some of those averages in the transactions themselves. So they're not essential for you to interpret those transactions, but they provide additional information. And some people would say that technically this is not data remediation, it's just improving quality, but it's usually done under the same circumstances. So in terms of actually performing data remediation, usually remediation follows data profiling and also follows the optional stage of cleansing and preprocessing. And some datasets at this stage are still going to be of low data quality and we have to improve them. You already know this. So usually, the process itself starts with identifying the missing values or the wrong values and why. Imagine that in our example, you have that list of sensor readings that have a 0 in terms of IoT instead of their correct value. Why did this happen at the end of the day? It's crucial to make sure that it doesn't happen again. Or in a data set of texts, we may have a lot of typos. Why did that happen? Did somebody type it manually? Did we curate the data or obtain it automatically from somebody else? Maybe a partner that didn't vet those texts, and so on. What is the reason? Then we have to figure out how to remedy the dataset. That is, what we're actually going to do. For example, for those values of 0 for the IoT readings, can we remove them? Or should we try and guess the temperatures at those points and replace them? Or if it's not temperature or pressure, something else? But at the end of the day, is it acceptable for us to try and guess those values? Should we remove those records? There's a lot of considerations that go here, right? For example, if the data set is a small data set and you almost don't have enough data, you may not want to remove those records. But at the same time, if you're guessing those values and you guess them wrong, because there's such a big proportion of the data set, that may be wrong as well. There's no right answer. It's just a matter of meeting with the business users and coming to a conclusion that is acceptable. Or for example, should we fix the typos in those texts? Or should we keep the typos and flag the texts as having typos explicitly to make the model resilient against typos? Because if you train a text model that is perfect and that doesn't know typos, it's not going to be able to interpret text that actually has typos. So again, there's pros and cons to each approach. There's no right answer. It's just about what is acceptable to the organization in each situation. And then we simply execute the measure and we use the new dataset, hopefully. As you see, data management is almost like a tool here, right? They meet with the organization says what they want them to do, and they simply execute those fixes in the data. So as we see, data remediation is all about identifying bad data. It's about identifying values that don't make sense and either replacing them or treating them in some other way. Let's talk a little bit about data governance and scale and its challenges. We've already covered that data governance is responsible for setting the principles and rules for data quality, data expectations, and so on. However, with higher data volume and complexity, with more use cases and other types of situations, data governance can kind of break or at least become less effective. Let's cover these challenges and how to address them. Welcome to this lesson on data governance at scale. So far, we've seen that data governance sets the expectations, the validity rules for data quality, the policies, and all of this is translated into specific requirements. But while this works at a local level, we may have issues as the organization grows. For example, we may have issues with data volume and data complexity. That is, especially if we're dealing with big data in data sets, it may be very intensive or even impossible to capture all of the data, profile all of the data, and remediate them. Can you use heuristics? Yes, but something is going to slip between the cracks. Or for example, maintaining data quality over time. We may have certain data that may become less relevant over time, such as fraud transaction data as new fraud types come out, or even image datasets with certain faces when beauty standards change, as we saw in the first lesson, and so on. We must ensure that the data quality remains high as time passes, which may be a challenge based on the types of data and how certain things change, society, technology, or any other element. Or for example, organizational silos or just corporate culture issues themselves. That is, you may have a data set that a team uses to train its AI model, and it may be useful for another team, but only if it's made available and captioned by those people, and they may not want to share. And if you don't have the authority to make them share it, then it's going to be an issue. And even if they share it, it's crucial to document the two different sets of features, use cases, and repositories. And finally, you may just have miscellaneous corporate culture issues. For example, people may just not care about data, they may not see their value, they may not want to use them even if they know the benefits, and others. So what data governance must do is ensure data quality across space and time. So what we have to do in data governance is we must ensure a high level of data quality across various teams, various uses, and as time goes by. For example, if you have different departments and different use cases for the data, for example, if you have a data set of photographs that is going to be used to train a new AI model that's completely different, and this AI model cares about the facial features in specific and not photography, then we need new features and we need new captions to exist in parallel with the current ones. Because one model just cares about the facial component of those features and the other model only cares about the photographical component of those features. And they must exist in parallel and with high data quality for the two sets of features. Then, across different locations as well. That is, different geographies may have different privacy or security requirements, so the same application may have to set different data policies for different geographies, and possibly for local repositories. Or you may even have something more intricate, such as, for example, in the future, AI regulation that prevents you from doing certain things with AI. For example, you may have AI that may not be used to generate a specific type of feature, such as with celebrities, but in another country, it may be okay. So you may have the same data set, but in one of them, you want to include photographs of celebrities, for example, and the associate captions, but for the other country, not at all. So you need to have the same data set for two different models with the same captions, but including or excluding specific types of data in that specific data set. Just an example, or you may have other use cases that are more advanced than this. And also, maintaining high data quality across different access levels. That is, different people may use data with different features masked, and we must have various views of the same data for various roles. For example, a database administrator may not need to see any fields at all. They just want to make sure that there is integrity in the records, there is backup scenarios, and so on. And you may have data analysts that are actually doing the profiling for a specific feature, and they need to see that feature, but maybe they don't need to see the other features. And you need to ensure high data quality of the dataset for those different uses. So as we see, as we use more data, or as we use the same data for additional use cases, it's important to maintain the same data quality rules, expectations, and principles for these new use cases, so that we can accommodate the new use cases without breaking the current ones. And with this, we reach the end of the Data Quality Enforcement module, where we focused on data quality, how to assess it, and how to enforce it. Let's cover the lessons that we took a look at, as well as the key takeaways for this module. We are now at the end of this third module on data quality enforcement. So what topics did we touch on in this module? Well, we talked about how data profiling is done by the data management team to detect biases or problems with datasets in general, and how data governance influences that operation. General principles translated into local principles translated into actual action. Then, how cleansing and preprocessing are two optional operations that can be applied to datasets to make them easier to handle and to reduce the noise inherent in them. Then, data remediation. Actions by data management that actually remove the problems and fix the issues that lower data quality, making data of higher quality and allowing them to be used for model training in a more effective manner. And finally, how data governance influences data-related operations at scale and the challenges that appear with various teams, various models, various geographies, and various datasets, and the need to maintain high data quality across all of these. Finally, what are some key takeaways from this module? First, data profiling aims to find missing values, biases, and other miscellaneous problems in datasets. As usual, we have a cascade. Data governance sets the general principles, data stewardship translates them to local rules and local principles, and data management executes the profiling and later remediation based on those. And remember that we have multiple dimensions: completeness, accuracy, uniqueness, timeliness, and so on. And one record may be of high quality according to one dimension and of low quality according to another one. Then, data cleansing reduces noise from data, such as outliers or wrong values, and data preprocessing makes the data more useful. They're both optional but valuable to use data in a more effective manner. And within data preprocessing, something which is very relevant is feature engineering, which consists of selecting or creating new features that most matter to us for model training, because the original features of the model may not be enough, and the new features that we may create are usually ratios or categories or binary flags of yes or no or normalizations of the current features by other values. Then, data remediation aims to fix the problems in data. It can remove or replace records, it can consolidate duplicates, it can resolve conflicts between contradictory entries, it can enrich entries for higher data quality, and more. And finally, data governance faces challenges at scale, such as using datasets by different teams with different purposes and different features, a high level of data volume or complexity, and possibly organizational issues themselves, such as silos or bad corporate culture. And remember that the imperative for data governance is to guarantee a high level of data quality across different teams, different purposes, different geographies, different access levels, and more. And with this, we closed this data quality enforcement module, where we focused on how to assess and maintain data quality. How to identify and treat biases in datasets. Let's take a look at the lessons from this module. Welcome to our fourth module, which is about data debiasing. So far, we've talked about data quality, but even if data have high quality, they can still have biases. And that's what we're going to cover in this module. Among other topics, we are going to cover, for example, how biases affect different AI models, including the consequences for both discriminative and generative models, as well as how biases can either be maintained or even made worse by AI models, and how to prevent it. Then, how data profiling helps detect biases in datasets, including in image, text, and structured data. Do notice that this is a different data profiling. It's not about data quality, it's about biases. So we use slightly different dimensions. But we'll get to that. Or, what are some ethical data dimensions to help detect biases in profiling? As we just mentioned, the dimensions that we're going to use are going to be different, and we're going to detect whether data are ethical or not according to high quality or not according to these dimensions. Or, for example, what are some bias mitigation strategies besides data profiling and remediation, such as diversifying datasets, training personnel, and so on? That is, besides the technical part, what else can we do? For that purpose, in this module, we are going to have 3 main lessons. The first is about bias in generative and discriminative AI. As the name indicates, we are just going to cover the outputs of generative and discriminative AI and how they are affected by biases, where do biases usually come from, in what form they can take, and what can possibly even make them worse, such as feedback loops. Then, our second lesson is about data profiling for data biases in specific. We are going to cover how data profiling can be used besides tracking data quality to actually track biases, or examples of overrepresented feature values and the ethical data dimensions that we use in this process. And finally, our third and last lesson has to do with bias mitigation strategies. That is, other actions that complement the data operations, the technical side, to mitigate biases, and also the role of synthetic data in de-biasing datasets, which can be a very powerful weapon. So as you see, this module is all about identifying biases, because even if datasets have high data quality, they may still have biases, and our goal is to tease them out and mitigate them. Let's talk a little bit about biases in generative versus discriminative AI. We may have biases due to a model or due to the data, but either way, when we have discriminative models, the biases usually reflect in decisions which classify something in the wrong way, while in generative models, usually the biases just affect the creations of that model. Let's talk a little bit about these considerations. Let's talk a little bit about bias in generative and discriminative AI. So when we talk about biases, they don't affect all AI models in the same manner. They manifest in different ways, and usually we split AI models into discriminative and generative, as you know. Discriminative models draw conclusions based on existing data, and generative models generate new data based on what they know. So, in discriminative AI, biases manifest by changing the decisions that we make based on the inputs. That is, overrepresentation of specific fraud in transactions can twist the way that the fraud is classified, or overrepresentation of specific diseases in medical histories can make the model unprepared for other types of conditions, or the overrepresentation of certain types of purchases may influence a model to only be able to make predictions based on those. But either way, the biases twist the classification or the outputs of discriminative models. In the case of generative AI, biases manifest in a different way, and that is by influencing the generations that the model makes. In other words, anything that is overrepresented in the training data is going to make its way, one way or another, into the final outputs. For example, overrepresentation of specific types of faces in image datasets, or certain vocabulary in text, or any other type of dominant feature is going to influence the model towards always producing that type of feature in final outputs. For example, if you train a text AI on academic articles with a very polished way of speaking, then almost all outputs of that model are going to have that polished way of speaking. That's why it's so important for any feature that you have to make sure that you have varied values in those features, because otherwise, certain values which are overrepresented are going to dominate the whole model. Unfortunately, something that has happened a lot historically is that certain models are overtrained on Caucasian data, which means that they cannot make decisions for other ethnicities. And in the case of generative AI, a lot of outputs are always going to be of white people. So this is the type of overrepresented value that we have to address in terms of biases. Now, biases come in all shapes and forms, right? They can either come from the data or from the model itself, from the training process or other processes. When they come from the data, it's pretty simple. That means that the data are already biased in some way. For example, a text dataset where 90% of texts are politically charged means that a model trained on them is going to be politically charged as well. Nothing new here. However, biases can also be in the model itself. For example, we may give too much weight to certain features in datasets, or we may overfit the model in training, or the architecture of the model itself may be biased. For example, if you have a dataset of pictures that contains studio pictures and normal pictures, if you will, casual ones, in equal quantity, but you train the model more on the polished pictures, which are studio pictures, then it's no wonder that the model is going to be biased towards producing studio pictures. So the biases can either come from the data or the way that we train the model with those data. And it's also important to understand that our model may make biases worse or not. Ideally, we want to mitigate biases, but in some cases, models can either maintain biases if they're not treated, or they can even make them worse. So a model is going to maintain a bias if it has simple outputs. That is, our only inputs are the original dataset and that's it. Any biases that exist are going to be propagated in a proportional manner. So in this case, the model may mitigate or just keep the biases in the data. Very simple. However, if we have feedback loops, that is, if our outputs are going to be treated as later inputs in terms of the model, then we are going to make the model biases worse. For example, if we have credit scores that are calculated which are biased, and those credit scores are later used as inputs for another model, then any biases that we propagate, for example, in terms of certain ethnicities or locations or financial statuses, are going to be made worse. In a way, we are recycling biased outputs to use them as inputs. So instead of keeping biases or mitigating them, we're amplifying them in reality. So as we see, biases behave in different ways when we're talking about discriminative or generative models. Whether the biases are due to the data or the model training itself, at the end of the day, biased generative models have a tendency to output more specific features in their creations, while biased discriminative models have a tendency to misclassify something based on specific biased features. Let's talk about data profiling for biases in specific. We've covered how to do data profiling for data quality in general, but here we're going to focus on dimensions that represent how ethical or varied something is. Let's take a look at this type of profiling. Welcome to this lesson on data profiling for data biases. As with other purposes, data profiling helps us identify biases. So data profiling is pretty much just using statistical and numerical methods to find out things about data. That's why it can detect data quality problems, it can detect biases, and a lot of other funny things that may be there. In this case, we can consider a bias, in a mathematical manner, the unequal distribution of values for a given feature. For example, if the Caucasian ethnicity is overrepresented in a feature, that just means that the distribution of possible values, which are the ethnicities, is not done in a balanced manner. So for image datasets, this can manifest as overrepresented values in terms of subject ethnicities, ages, genders, backgrounds, poses by models, picture quality, the picture styles or drawing styles, professional versus casual photographs, and a lot more. And it may be biased according to many of these dimensions. For example, if you only have pictures of one person at a time, you're not going to be able to generate pictures that have two or more people. Or if you only have pictures that are studio quality or high quality, you're not going to be able to generate those casual, low quality pictures such as taken from a smartphone, and so on. The dataset may be biased according to many of these features, or all. Then, for text datasets, we may have overrepresented values in terms of the tone of the text, political bias, vocabulary, truth or not. That is, if the text is fake, you're going to introduce false facts into the model, text sentiment, or dialect. Again, you may be biased according to many of these. For example, if you train a text model like an LLM on a set of text articles which are politically biased and have false facts, then that model is going to learn fake facts and it's going to be politically charged. Again, many of these features may have biases. And for example, for numerical or structured datasets, you can have overrepresented values in terms of situations. For example, one type of transaction in financial transactions, one type of debt in credit scores, one type of location in terms of clients, one type of purchase, and so on. Or values, for example, for a sales dataset, you may only have high-ticket items or low-ticket purchases, and many others. Now, in terms of the consequences of bias, it's important to understand that biases are not always obvious, and they may not become apparent unless we actively profile for them and examine them. There are a lot of datasets where you may think, oh, this dataset is balanced, but then somebody finally remembers to do data profiling and they realize, oh no, it's not balanced at all. So bias can be very subtle. So imagine, for example, that there is a slight bias against a country in texts, and you're training a text AI. There's nothing apparently wrong with the texts except that when a certain country comes up, negative words are associated with that country, and everything else seems okay. Then you train an LLM on it, and you try to talk about that country, and then you wonder why it's discriminating, okay? So a lot of biases can be very subtle and just pop up in certain situations. In the example that I just gave, if you train an image dataset on photos that just have one people, unless you try to actively generate a photo with two people at once, you're never going to realize that. Or in a related example to the one that we just mentioned, imagine that there's a slight bias towards front view portraits in image. That is, all pictures that you have of models or people are front-facing. You don't have any side view, three-quarters view, and so on. So most images in that portrait dataset are of the person facing the camera, facing forward. Well, you train an image model and then you wonder why you can't do a side view of any person, for example. And again, unless you actively try to hunt for this and find those biases, you're not going to realize them. And again, this is why it's so important to do feature engineering, because if the pose of the face is something essential, if you want to be able to generate faces in different poses, then that must be a key feature, because that way you would have been aware of the feature distribution in terms of values from day one once you're curating the dataset. And you don't have to find that out at this stage. Now, just like we have data quality dimensions to calculate whether a dataset has high quality or low quality for specific fields or specific features in terms of values, we also have ethical data dimensions. These are different, and they indicate whether a dataset has high quality or low quality according to certain ethical parameters. So for example, one of them is variety, that is, how representative this specific feature value is. For example, how many times does this value repeat in the dataset out of the total values? The usual example is ethnicity, because unfortunately it's a very prevalent type of bias. So for every value, such as for example, Caucasian person, Black person, what is the representation of this specific value across the whole universe of values for this feature? And then, based on the variety of every single value for that feature, such as for example ethnicity, it's easy to know whether you have bias or not. Another one is fairness, that is, how similar this decision is to other decisions. This is for specific database fields or values in terms of features which are decisions or results, such as, for example, for a credit score, the result in terms of the credit score, or for fraud situations in the past, whether this was flagged as fraud or not. And in this case, what you want to calculate is whether this specific decision is the same for similar situations. So for example, if we have a given credit score number, is the credit score similar to other credit scores of subjects with different ages, locations, or ethnicities? That is, if you have a young person and an old person where every other database field is the same, is the credit score the same? Or does the credit score just have a minor fluctuation regarding that small fluctuation in the age itself, or is it radically different? That represents how fair those decisions are, or those values for that feature. Or for example, auditability. That is, how transparent is this dataset? So for example, if we have a list of scientific articles or news articles to train a text generative AI LLM, can we audit them? Do we have sources for them? What do we know about the authors and the methods? In other words, how transparent are the data in terms of the underlying facts? Because the less transparent they are, the higher the risk that we're training on fake data. As we see, different types of mediums can have different types of biases, but at the end of the day, ethical data dimensions like variety, fairness, or auditability allow you to really know whether a specific dataset has high data quality or not according to that specific ethical dimension, which means that it's biased or not. Let's talk a little bit about bias mitigation strategies without involving profiling and remediation. That is, you may already have a pipeline for profiling data and remediating the biases, but at the end of the day, are there more things that you can do so that the data are not even biased in the first place? Yes, there are, such as collecting data from multiple sources, training people, using synthetic data, and so on. Let's cover these alternative or complementary measures to reduce bias in your datasets. Welcome to this lesson on bias mitigation strategies besides the data operations themselves. So, in terms of mitigating biases, data profiling and later data remediation are at the core of this process. I'm not contesting that. However, are there other things that we can do to supplement this strategy and to mitigate biases? Absolutely. For a full strategy, we may want to consider other additional things, such as, for example, collecting data from various sources. That That is, assuming that the quality remains the same, we can collect data from various sources because they complement each other, and because the sources are varied, we are likely to have less bias. For example, collecting scientific articles from multiple universities, or news articles from multiple sources, or photographs from multiple websites or portfolios, or transactions from multiple merchants, and so on. It helps us get out of our bubble, because here's the thing. When we have a dataset, we may be sure that we have no biases within that dataset, but there may be features that we're not even aware of because we don't even know what's out there. But when we obtain a second dataset of the same type, we can compare and we finally know, oh, one of these datasets is very skewed in terms of this feature. So the more datasets that you can collect, and again, assuming the quality is the same, the better. Or for example, doing preliminary statistical analysis. That is, before diving deep into full-fledged data profiling or data management initiatives, some automated tools can analyze the incoming data and their features. For example, you're considering purchasing data from a provider, and you already know what are the key features to train your model because data stewardship has done a very good job. So what to do is the partner or possible partner sends you a sample, and you may run some kind of automated analysis just with some heuristical parameters to know, hey, do we have price-worthy transactions, do we have location, and so on. And it immediately tells you, hey, does this data set appear to be of high quality according to the features that we need or not at all? And that can help you make more informed decisions. Or on the other hand, go back to the partner and tell them, hey folks, we need something different before you even acquire the data set, which is going to save you a lot of work in terms of needing to profile and remediate the data later on. Or, for example, investing in stakeholder training and awareness. In other words, in less fancy language, if the people that are training the model or that deal with the data don't care about the data, then nothing else matters because you're not going to get anything done. So educating people at all levels, business users, executives, about the importance of data, what happens with biases, and the economical impact of all of this is going to be very important. Now, one measure which is very important in terms of reducing biases in data is synthetic data. Synthetic data works in many cases to augment datasets and to complement the biases and faults of those datasets. Synthetic data, just a reminder, is creating artificial data that have similar characteristics to the data that you already have. And this is especially important when the data have biases. For example, if you have a list of customers and 20 customers have a specific type of fraud occurring in their accounts and other 2 customers have another type of fraud, then that type of fraud, which only has 2 records, is underrepresented. So what you can do is you can create synthetic data that is creating false customers which have similar details to the existing ones with a second type of fraud, so that you can create, for example, 18 more records, and now you have 20 records of one type of fraud and 20 records of another type of fraud. For text data or structured data, this is very easy to do, for example, with ChatGPT or an LLM. You just plug in the records and you say, hey, can you create more records which are artificial like these? We'll get to that. But the key is creating synthetic data depends on the medium. So for example, if you have numerical or structured data, as I mentioned, it's very easy to create. You have a list of structured features, usually with a set of options or a range, and you can easily create new entries based on these. In many cases, you don't even need an LLM. You can literally just create new records and type in the data by yourself, as long as all features continue having a balanced representation in terms of their values. Then, for text data in specific, it's still easy, but it's a little bit harder. It has some caveats. So we can use an LLM, for example, to ingest text and produce more text in the same style, or even do it with numerical and structured data, but you need to be aware of hallucinations in generative AI. But if everything is okay and you have checked the new records for facts and the data profiling still tells you that the values have equal representation, then that's fine. But do be aware of this small setback of LLMs. And finally, for image data, this is the hardest type. What we can do is maybe train a quick generative model to generate pictures in the same style, and then use this model or the pictures generated with it to train the true generative image model. So let's say that you're trying to train an image model on, for example, classical Flanders paintings in order to generate more oil paintings, but you only have 4 of them. So what you can do is, instead of training the true model, you can train a quick model just to try and generate more pictures that seem like oil paintings, and you can just run a numbers game and generate thousands of pictures until you get acceptable ones that really look like the original oil paintings. And then once you have 10 or 20 of those, then you can add them to the original pictures, and now you have a data set of 14 or 24 pictures. And now you can train the full-fledged image generative model. So for each one of these formats of data, it gets harder and harder, but it's never impossible. So as we see, we have a couple of measures that are complementary to the usual profiling and remediation pipeline. And in specific, when it comes to synthetic data, they are very valuable, but it's important to be aware of how easy they are to create based on the medium of the data that we have. With this, we reach the end of the data debiasing module, where we focused on how to identify and how to eradicate or just mitigate biases in our datasets. Let's recap the lessons and key takeaways. We are now at the end of our fourth module on data debiasing. In this module, we touched on topics such as, for example, how bias affects AI models, including the consequences for generative and discriminative models, as well as how biases can be mitigated, maintained, or made even worse depending on what we do with the model. Then, how data profiling, besides tracking data quality issues, also helps detect biases in datasets, including in image, text, and structured data, examples of features, or what are some ethical data dimensions to help detect biases in profiling. That is, disregarding the dimensions for data quality problem identification, what are the specific dimensions to identify biases? Or what are some bias mitigation strategies besides data profiling and remediation, varying the data sources, training personnel, or using synthetic data? What are some key takeaways from this module? First, biases affect discriminative models by twisting their conclusions or classifications, and they twist generative models by influencing the outputs. Then, biases can exist in the data or the training process, and if we have feedback loops, that is, current outputs used as future inputs, they even worsen biases. Then, we profile for data biases by detecting overrepresented feature values, and for this, we use ethical dimensions such as variety, fairness, or auditability, which help us identify data quality issues in terms of ethics in specific. By the way, I'm using biases and ethics in an interchangeable manner, but at the end of the day, what we mean is there's data quality in terms of whether a dataset is biased or not, and if it's ethical, it usually doesn't have biases and vice versa. Then, we can also mitigate biases with other actions besides profiling itself, as we mentioned, varying the data sources, doing preliminary statistical analysis of the data sources before we ingest them, and making stakeholders be aware of the consequences of not managing data well, and biases. And finally, synthetic data can help balance biases in datasets. It is used to augment datasets, that is, to obtain more data of some type that we don't have. It's very easy to do for numerical or structured data, it's less easy to do for text data, and it's harder to do for image data. And with this, we close the data debiasing module, where our major goal was to focus on how to assess and eliminate bias in datasets. Welcome to the Data Security and Privacy module. For a lot of specialists, data security and privacy are a bit boring, right? They think, hey, give me the AI, give me the data, those are the things that interest me. But because we process a lot of personal data or data in high volumes, we really need to focus on data security and privacy, especially in data governance, because it's literally a part of it. Let's take a look at some topics related to data security and privacy. Welcome to module number 5 on data security and privacy. In this module, we are going to focus on topics such as, for example, what are some protection techniques for training data, both in the physical and the digital worlds of various types? How to encrypt them, how to actually protect them, limit access, and a lot more. Or, for example, what are some measures to de-identify and redact personally identifiable information, or PII, so that we can safely process them without fear of leaking personal elements? Or defining access control measures for training data to users by their role, because different users are going to use the data for different purposes, and they should not have access to the same properties of the data or the data themselves. Each person has a specific purpose. Or, for example, defining how regulation affects which data we can keep, for how long, when we can discard that data, and other measures such as security controls that may be mandated, and which ones apply to you. For this purpose, we are going to have 4 distinct lessons in this module. The first lesson is about data protection techniques. And as the name says, it's about measures to protect data, including physical and logical measures, minimizing the data that we collect, and other measures to make sure that training data are as protected as can be. Then, lesson number 2 is about protecting personally identifiable information, or PII. That is, how to safely process these data to protect the data subjects when we deal with these types of data, such as health information or financial information that contain very sensitive personal elements. Then, lesson number 3 is about access control by role. That is, principles to limit access to the data by what the users need to see and how they need to interact with the data. Different roles may need to have access to different values of the database, and what we can do is we can hide other values of the data that they don't need to see, because a person should only see the minimum bare possible in order to properly do their job. And finally, lesson number 4 is about relevant regulation. That is, how different regulatory frameworks like the GDPR, FISMA, HIPAA, PCI DSS, and so on may impact which data we can collect, for how long, how we must get rid of it, what data to destroy, what rights the data subjects have, such as the right to be forgotten or not discriminated, among many other possible measures that may be mandated by regulation. So as we see, we are going to cover different aspects of how to keep AI training data safe in one way or another. Let's talk a little bit about data protection measures. We're not going to go too deep, but it's important to be aware of what elements contribute to protecting your data. For example, minimizing the data that you collect is a great way to not have to protect them, or destroying them according to a specific timeline, or just having logical and physical protection measures, among other measures. Let's take a look at how to protect your data in general. Welcome to this lesson on data protection techniques. Training data, just like any other type of data in an organization, must be kept safe. In this sense, they're not that different, so the measures that we can use to protect these data are varied, and they can include, first, physical and logical protection. This is what you usually think of when you think about protecting data. It's about protecting data physically, such as with locked rooms, lockers, security guards, CCTV, or logical, in the digital world, with encryption, VPNs, firewall, access control, and a lot more. Then, another measure is data minimization. Here's the thing. The best way to protect data is to not even keep them in the first place, so we should keep as little data as possible. The more data that we have, the more that we need to protect, and the harsher the consequences of a breach or a security incident. Naturally, organizations have a tendency to collect all data possible, but what we should do is we should plan the models that we need to train both in the present and the near future, and just collect the bare minimum data in order to train them. Because remember, there's always a trade-off between the gains of training specific models with a large quantity of data and the consequences in negative terms of security breaches or incidents. Then, another measure is destruction processes and timelines. That is, the data that we collect must be destroyed after a certain period. Certain categories of data, such as health data or financial data, usually due to regulation, have a specific time frame for existing, such as, for example, 2 years. After 2 years, they must be destroyed immediately. But on the other hand, they must be maintained for those 2 years. And the different time frames may change based on regulation and the types of data. And the data may also need to be destroyed with certain methods, such as, for example, erasing with zeros specific hard drives or other types of storage, or we may need to burn or destroy or demagnetize hard drives or other types of physical equipment, and so on. It all depends on the regulation and the types of data. And finally, access control is another measure. That is, different people should only access the parts of data that they need to. Not everybody in an organization should have carte blanche to access any data that they want. That is a very dangerous principle. So we should do the exact opposite. Every person should see the minimum amount of data that they need and for the minimum amount of time that is necessary. Now, diving into some logical and physical protection measures. As with other data types, the protection measures that apply here are either logical or physical. That is, in the digital world or the physical one. We start with physical protection. And as we mentioned, these are measures in the real world. It's about limiting access to facilities and to devices, locking rooms, locking server racks, having surveillance, having mechanisms against tampering of hardware, and so on. Usually, we must inventory all physical devices, including storage ones, and we must keep track of all movement, especially outside the organization. That is, if somebody takes a hard drive with sensitive information outside the organization for repair, we must know exactly where it is, we must know exactly who has access to it and for how long, or even within the organization. Where is it in terms of the room? Do the people that access that room have access to the data that is in that hard disk? That is, do they have enough permissions in terms of their role? And if not, then something is wrong. Everything has to be coordinated. Data have different levels of sensitivity, and the people who are accessing the data should be the only ones that are allowed to view those data. Nobody should be seeing data or accessing devices that are beyond their permissions. And another measure, for example, is that all unneeded devices, ports, and facilities should be closed or not used. For example, ports in applications that are not needed are just a security vulnerability waiting to be exploited. And by that same token, devices that we don't need to use should not be turned on, or even worse, connected to the network just waiting to be exploited. These are just good security practices. Then, in terms of the digital world, that is logical protection, we should encrypt all data that we have, ideally with split key measures. That is, one key is split across two people, so that if one person is compromised, then the hacker doesn't have access to the encryption key. And keys, for example, should be rotated with time, and they should be strong. And the same with passwords, obviously. You don't want any weak links in terms of encryption. And naturally, cybersecurity also matters. Intrusion prevention systems or intrusion detection systems, firewalls, VPNs, and all those types of security measures. Or regular penetration testing and vulnerability audits, for example, are also very important. And data should be partially hidden. That is, masking, hashing, tokenizing, and others can let people work with data without seeing the data. For example, if you have a list of customers and somebody is trying to calculate something related to the prices or fraud, they don't really need to see the name of the person or the address. Or maybe they only need to see the location at an aggregated level. So what you can do is, for example, you can mask those fields so that they can't see those fields. So they know the records that they're working with, but they don't know the specific name of a person or their home address, for example. So as we see, we have measures such as data protection measures, which are usually the most obvious ones, such as protecting data in the logical world and the physical world, but we also have other measures such as minimizing the data that we collect or destroying them with specific timelines. All of these help protect your data. Let's talk about how to process PII, or personally identifiable information. This can be names, addresses, health information, financial information, and more. This is interesting because a lot of the models, I would even argue the most valuable models in terms of AI, have to use personal information. But this means that we need to step up our game when it comes to security and privacy techniques, and we have specific ones for PII. Let's take a look. Welcome to this lesson on processing PII, personally identifiable information. Personally identifiable information, or PII, is any type of information that includes sensitive details about a person's life, health information, financial information, and so on. And these types of data present unique challenges, and they demand unique measures to protect them. If you're training models that deal with financial information, credit scores, detecting diseases, and so on, the level of data in those models is a lot more sensitive and intimate than the data, for example, in a news article text generative AI. It's completely different. And due to the added level of sensitivity in this type of data, we also have an added level of demand in terms of protecting these data. And measures can include, for example, de-identification. As the name says, we mask or tokenize essential fields, for example. In our example, where somebody is dealing with financial information, but they don't need to see the names of the customers, we can mask the names, or we can hash them or tokenize them. For example, the name John Smith becomes a simple code like A413. So you know that you're dealing with user A413, but you don't really know what is their real name. And we can do the same for all essential fields, such as credit card numbers, addresses, names, and other types of sensitive fields. Another measure is noise insertion. And what we do here is we modify personal fields to hide details without affecting the training. So for example, if we're training a model for credit scores in an area such as, for example, California, and we have addresses in terms of San Francisco or Los Angeles, we can replace the addresses just with California. We are disturbing the addresses, but it doesn't matter because for what the model is learning, it doesn't make a lot of difference. Or for any address, we can literally replace the address with San Francisco or Los Angeles. So every address is going to be from one of those two areas. We don't know, but it doesn't really make a difference for what the model is learning. And by the way, this also introduces an interesting point, which is you can only introduce noise to a point where it doesn't disturb the actual model. So for example, if you want to calculate credit scores with a high level of granularity, such as at the street level or county level, then you can't do this. So in other words, you can introduce the maximum level of noise possible in a field that does not disturb the features that are going to be learned by the model itself. Another technique is advanced anonymity. So we have methods like k-anonymity or L-diversity, and these are more complex numerical formulas and mathematical formulas. But at the end of the day, what they consist of is the following. If you have a list of, for example, 10 subjects, and 9 of them have a specific condition and only one of them has another condition, then in that dataset you know that if a person has that condition, it's that specific person. And it also depends on the relationship with other values. So for example, if all people with a certain condition are from one city, then you already know that if somebody has that condition, they are from a specific city. So what you want to do is you want to balance the ratios between feature values so that if you know a specific address or a specific medical condition, in this example, it doesn't tell you anything else about the data. So these are advanced methods to maintain those ratios so that knowing a specific feature value doesn't tell you anything. So defining this more formally, we ensure that specific details in a group do not reveal belonging to that group or that a relative frequency of a feature value is low. And then another measure is synthetic data creation. So we talked about how these can be used to fight biases, but they can also be used to actually remove personal elements. So what we do is, based on the real data that we have, we create similar synthetic data with similar names, similar addresses, similar credit scores, similar photography styles, whatever is in the dataset, which are not real elements, but that seem like real elements. So for example, if you have a list of 20 records of credit scores from people in California, you create other 20 people which are artificial, but they have similar addresses, similar credit scores, and similar properties. They're not real. So if the data are weak, there's no real consequence. But for model training, the dataset is practically the same, because the feature values are very similar to the real ones. In other words, you create fake people which are very similar to the real people that you have, or similar elements of the dataset for any other type of dataset. So out of curiosity, how does this work in practice? How do you hide personal details, de-identify data, or redact the personal elements? Well, imagine that we have specific names such as client names in a dataset. What we do is, for example, we hash the names. So we replace every single name with a code. So John Smith becomes H361A3, for example. And then the people who are working with that specific record know who that person is because the code is unique, but they don't know the person's name. So they don't see any information that they don't need to. We can also use masking, which literally hides that field. So the name becomes an empty string for everybody. So people who are working with the records just see empty names. Noise insertion, as we mentioned, replaces small details, such as replacing John Smith with Jack Smith. So insert a level of noise that disturbs real details so that the person's information cannot be compromised, but it's still a detail that makes sense and the data are not really that different. It doesn't make any difference for the purpose of model training or working with the data, but it's different enough to reduce the consequences of a breach or a leak. And the goal here is for the specific details to be hidden, but the big picture of the data to still make sense. In other words, the dataset is virtually the same from a bird's eye view, but if you zoom in on any specific field, you can't really pinpoint it to a specific name or address or any other type of value. And this allows, for example, professionals to work with individual records for data profiling purposes or data remediation and so on without actually knowing who the person is. Or again, in the case of a leak or a security incident, the hackers have nothing. And do notice here that we're going to talk about this in access control, but different professionals need access to different fields. So for example, if somebody is dealing with a transaction data set and they need to do data profiling on the specific financials, they don't need to see the names or addresses. But later on, a different data management team may need to do data profiling just on the names. And in that case, you can mask everything else or hash everything else, but you need to keep the names. So different roles need to have access to different values within a dataset, and you can hide all other details that they don't need. So as we see, we have many ways to protect personally identifiable information. We can mask, we can hash, we can tokenize, we can use advanced anonymity techniques, but at the end of the day, what we're doing is we're taking a dataset and just redacting in a way the confidential information or sensitive information so that we can keep processing the data without exposing those personal details in case of a breach or just the people who should not know about this information. Let's talk about access control by role. A lot of people focus on protecting data from outside sources, but they don't even think about protecting data from inside sources as well. Not everybody in your organization, all types of roles, should have full unbridled access to all datasets. Usually, what you want to do is you want to define what specific roles have to do with specific tasks and then only give them access to the bare minimum data that they need in order to do their job, what we call the principle of least privilege. Let's take a look at these principles. Welcome to this lesson on access control by role. When you have training data in an organization, a lot of different roles are going to need to work with that data. That is basic. However, what you want to do is you want to give the least access possible to those data for the least amount of time possible and to the least amount of people possible. This is consolidated as the POLP, or the principle of least privilege in cybersecurity. This is a cybersecurity principle that defends that people should have access to the minimum possible in order to perform their tasks. If you've ever seen one of those spy movies where people say, this is on a need-to-know basis, this is the digital equivalent in terms of data. You only see the data that you need to for the minimum amount of time. And when limiting access to the data, we need to take into account several factors. The first is, what does each role need from those data? Do they need to view the whole data? Do they need to edit data? Do they need to see the whole fields or not at all? and so on. Or for example, should they have access to all of the records or just the specific fields? Or how long do they need access for, and how frequently? Is it a one-time project? Is it somebody that needs to monitor data 24/7 or once per month? What is the specific duration of their operation on data, and is it recurrent or not? And this is what we call access control, right? Access control to the data according to the specific user role. And here, access control usually sits at the intersection of data governance and information security. Security and privacy are a part of data governance, but usually you are also going to have some sort of outfit in your organization, such as an information security department that takes care of this. So access control is usually a collaboration between these two departments. And as with many other areas, the data stewards also help translate these to specific data sources. For example, if you have a mandate to hide personal data in terms of data governance, that's very generic. How do you translate it to every single team and every single database? Well, the data steward may work with the business users and with the information security professionals to define what is going to be hidden from whom in that specific repository. So for example, how does it apply to a patient dataset, to a credit card dataset, and for the different roles they need to view and work with those data? It may be interesting to consolidate this with some specific roles. So access control naturally depends on the specific roles that need access to the data. You may have, for example, data managers or data engineers, and these people need to find and fix the bad data. They need to work with them. They usually need access to the raw data that usually comes direct from the source, maybe even before the pre-processing, and it depends on the data profiling and remediation initiative. That is, are we trying to fix all errors or errors in just a specific feature? And they need to both profile the issues and remediate the issues. Another profile are data scientists. These usually are just drawing conclusions in training models. That is, they take the raw data and they want to extract insights from them. Usually, they only need access to the finalized data sets that are used for the model training. Because they don't need to intervene, they just want to draw conclusions just like what the model would be learning from the data. Then you have security administrators, such as a database administrator. And these may need to implement security measures and monitor breaches. So usually they may not need to access the data, just the metadata, such as the logs or the security audits or reports. In other words, they just want to protect the database, for example. They don't need to actually go into it. Then another role are the business users. In many cases, these just want to draw conclusions from the data. For example, hey, if we're going to train a model on this data set of credit scores, can I take a look at the credit scores just to see what we have here? Usually, they just access the reports or the data products. That is, for example, a report on the data set instead of the data set itself, and they don't access the data itself. So as we see, not all roles need to see all database fields. Some of them may not even need to see any at all. So it's very important to define what each role may be able to see and for what purpose, because you never want to give more access to data to people than the bare minimum access that they need to do their job. Let's talk about relevant regulatory frameworks. Especially in data governance, it's paramount to be aware and keep up to date on the regulation that may affect you, because we've all heard of regulatory frameworks like GDPR, HIPAA, FISMA, PCI DSS, and so on. But what do they actually mean for us? They may affect the data that we may collect, how we may use them, when we have to destroy them, or when we have to keep them, or when we have to keep them and then immediately after destroy them, the security controls that we must use, and other possibilities. Let's take a look at how regulation affects us. Welcome to this lesson on relevant regulation. Regulation is very pervasive and very important when dealing with training data. It may affect multiple aspects of our training data and pretty much all the data in our organization. For example, regulation may define which data we can even collect in the first place. Certain frameworks, such as the GDPR, may prevent collecting data if you don't have lawful consent for a specific purpose. Others, such as the CCPA, are similar, but they may allow collecting of the data without authorization, but then the data subject or user can contact you afterwards and opt out of the collection of those data, and then you have to delete them. So you may have data that you cannot even collect in the first place, or that you can collect but must delete later upon request. For example, regulation may also define for how long data can be collected or must be collected. Frameworks such as the GDPR mandate the immediate destruction of data if the data subject requests it. And you may also have other types of regulation, such as specific healthcare and finance regulation, that may mandate specific retention periods. For example, in terms of lending regulation in the realm of finance, it may be frequent for certain decisions, if they're made by an algorithm, such as loan decisions, that regulation may mandate that you save all loan decisions from 2 years or 3 years back or even more, and not only that, but all inputs at the time that were used to make a decision. So you may have regulation that tells you that you must keep data for a certain period of time, and other regulation that tells you that you must delete data after that period of time, or immediately upon request. Then, regulation may also define which data must be kept. As we mentioned, certain frameworks such as the Equal Credit Opportunity Act may demand that model decisions be saved, such as loan decisions, along with all data taken into account to make that decision. So we have this conflict here because you may have regulation that tells you to keep certain data or to destroy those data, or you may even have a situation where you must keep certain data for a period of time, such as 2 years, but then you must delete those data immediately after those 2 years. It depends on what types of regulation affect you and specific datasets. Do notice that regulation may apply to different datasets. For example, if you have a company where you have loan decisions and other types of financial information, then you may have datasets regarding loan decisions that are affected and subject to certain timeframes, and you may have other datasets that are not subject to those timeframes at all. This is another testament to the importance of data governance and data stewardship. You have to know exactly what datasets you have, what is the type of data contained in them, and what timeframes each one of them is subject to. Now, this may be obvious, but regulation varies. That is, only a dedicated legal team can tell you exactly what regulatory frameworks apply to you in this moment for this specific activity. I cannot teach you this in general in this course. However, I can give you examples of usual regulatory frameworks and their consequences. So for example, we may have the GDPR or General Data Protection Regulation. That is, if you do business in the European Union, there are strict rules on data handling, the data that you can collect, and storing those data. You require lawful consent to process personal data, and you may also need to delete those data upon request. You may not need to, you actually need to. You also have the CCPA, or California Consumer Privacy Act. It's very similar to the GDPR in many ways, but it has some slight differences. For example, it doesn't prevent the unlawful collection of data, it just tells you that if the data subject afterwards wants to opt out, they can opt out. And it has certain rights, such as the right to not be discriminated, which is explicit in the CCPA. In the GDPR, it's not that explicit. So under the CCPA, a data subject may actively protest if they think that a certain decision was not fair to them and may request clarifications, while in the GDPR, not exactly. Then you have the HIPAA, or Health Insurance Portability and Accountability Act. And this type of regulation requires the protection and confidential handling of health data, or PHI, or personal health information as it's formally called. So it required certain security controls and the labeling of confidential data as confidential data for this purpose. It requires certain risk assessments, regular audits of your security and privacy controls, and other types of safeguards. Then you have, for example, the PCI DSS, or the Payment Card Industry Data Security Standards. It's important to notice that in this case, this is not legal regulation, it's industry regulation. That is, it's not a government that is mandating you to apply this regulation. You can decide to opt in or not, but if you don't, then a lot of consumers are not going to trust you. But for a lot of purposes, it's exactly the same. You have to obey it. And in this case, this type of regulation usually requires the secure handling of credit card data with strong security demands in terms of networks, storage, communication, and so on. The PCI DSS are actually a security tour de force. They mandate all types of security controls in terms of encryption, secure communication, secure storage in the real world and digital, and a lot more. And naturally, you may have other types of regulatory frameworks apply to you, such as FISMA for US federal agencies, including demands in terms of encryption and security protocols, or the Sarbanes-Oxley Act in terms of corporate finance, in terms of the financial information that you keep, and a lot more. So I'm just trying to illustrate how different types of regulation may have different requirements in terms of the data that you can keep, the security controls that you have to use to protect them, how you must classify them, and a lot more. At the end of the day, naturally, only a specialized legal team can tell you how regulation affects data governance, but in general terms, it's important for everybody to be aware that there may be regulatory frameworks affecting how you collect every single dataset that you have, how long you can keep it, when you have to dispose of it, how you must redact specific data, the security controls that you must use, and other possibilities. It all comes down to which specific regulatory frameworks are affecting you in this moment. With this, we reach the end of the data security and privacy module, where we covered security controls, access control, personal information, regulation, and more. Let's recap the topics from this module as well as some key takeaways. And with this, we reach the end of this 5th module on data security and privacy. In this module, we touched on a couple of topics. First, we talked about protection techniques for training data, or data in general, because there's not a lot of difference in this case, both in the physical and digital worlds of various types. Minimizing the data that you collect, logical security controls, physical security controls, access control, and a lot more. Then, measures to de-identify and redact personally identifiable information, or PII, in training data to safely process them, such as masking, hashing, tokenizing, and so on. In other words, protecting the confidential parts of that information. Then, defining access control for training data to users by role based on their needed level of access to the data. That is, giving people the least amount of access possible for the least amount of time possible, but figuring out what that is for each specific role. And then just defining how regulation can affect the types of data that you can keep and for how long, as well as the main types of regulation that may affect you. What are some of the key takeaways from this course? Well, to protect data, we can use physical security measures or logical security measures. Physical measures are things like locked rooms, locked server racks, CCTV, and so on. Logical measures are things like encryption, firewalls, cybersecurity, and so on. Besides these direct security measures, other measures like limiting access by user role, having timelines to destroy data, and minimizing the data collection also help here. Then, we must protect the sensitive elements in personally identifiable information, the confidential part of data that is very personal and intimate. We can de-identify the data that is hiding or changing those specific fields. We can insert noise so that they're not recognizable. We can guarantee advanced anonymity with ratios or specific correlations between values of different features, or we can create synthetic data to never use PII in the first place. Then, we should limit access to the data. That is, users should see the bare minimum in order to do their job, the POLP, or principle of least privilege. And these permissions sit at the intersection of data governance and information security, so usually there's always some sort of collaboration between these two teams. And finally, regulatory frameworks may affect a lot of the work that you do, which data you can collect, how you can process those data, for how long you can keep them, how soon we must destroy them afterwards, and specific security controls or processes used to protect those data. And remember that different frameworks have different demands, in that one framework may not apply to all the data within your organization. It may only apply to specific data that may be in scope of that regulatory framework. And with this, we close the data security and privacy module, which was all about, in general, in an overview, how to keep your AI training dataset safe. Welcome to the 6th module on full run-throughs. In this module, we are going to cover specific examples of how to use all of the techniques that we've covered so far for specific examples, how to train specific types of models with specific datasets. Let's take a look at the lessons and goals that we're going to have in this module. Welcome to the 6th module on full run-throughs, where we are going to cover examples of everything that we've covered so far, from data quality issues, biases, security, privacy, and more for specific examples. So in this module, what are we going to focus on? For example, we are going to focus on specific examples for specific types of AI, generative and discriminative, with various media types, and with specific data formats as well. Or the various problems that can occur at all stages related to data quality, to biases, harmonizing datasets, metadata, and more, as well as naturally the possible fixes for each one of these. Or illustrating the various processes that we've covered in this course, such as data profiling, data remediation, mitigating biases, and others, but for specific applications. For this purpose, we are going to have 3 main lessons in this module. So the first lesson is about creating a generative AI model for logo generation in terms of image. So we are going to deal with curating datasets of existing logos, dealing with issues related to watermark and low resolution in images, debiasing colors that may be overrepresented, and just ensuring the privacy and security of our data, the logos in this case. Then, our second lesson is going to be about a generative AI model as well, but in terms of text for knowledge-based use, both for external users and also for internal users with 2 datasets with different levels of sensitivity. So again, we're going to talk about curating datasets of text, dealing with conflicting and outdated information, for example about products or manuals, about debiasing jargon in specific topics in datasets, There is certain topics like sales may be overrepresented, or a lot of the text may be technical, so the level of jargon is overrepresented as well, and just ensuring the security and privacy of our text data. And finally, our third lesson will be about creating a discriminative AI model for fraudulent transaction classification. More typical use case, if you will. So we're going to talk about curating datasets of fraudulent transactions, dealing with transactions that may have no dollar value or that may have the wrong categories, debiasing location and fraud types that may be overrepresented in the data, and just ensuring the security and privacy of these data at the end of the day. So as you see, this module is all about making it real and crystallizing the techniques and everything that we've talked about with very specific examples. Let's cover an example of training a generative AI in terms of image to generate logos. We are going to cover what are the usual challenges in terms of curating data, data quality issues, biases, and security and privacy controls for this very specific use case. Let's take a look. So let's cover an example of training a generative AI model and managing the training data specifically for generating a logo, a simple logo in visual terms. So in our company, we decide, or somebody has decided, to start generating logos with AI. So for this purpose, we are going to need to gather the data, ensure that the datasets are optimal, and actually train the AI using these data. Nothing new here. And we are going to go through the usual steps that we've covered in this course, right? So first, curating or obtaining the logos in some way, then profiling for data quality issues and remedying those issues if they exist, then doing exactly the same for biases in the data. That is, after the data have high data quality, they may still have biases, and we are going to hunt for them to make sure that our model is not going to be unbalanced in terms of outputs. And last but not least, always enforcing security and privacy in our training data. So the first step is curating or obtaining the data, as always. So we decide to curate logos from multiple sources, and these may include past logos from our organizations or that were hired by somebody else to do them, but we own that IP, or from open source repositories as well, and from licensed databases. So we have a variety of logos here with a variety of colors and sectors and themes to actually train our AI. And one thing which is important is that since it was not specified what type of logo leadership wants to generate, and this is a frequent occurrence, we make sure to gather logos with a variety of styles and color schemes, right? Because we want to have a model that is more generalistic and not that much specialized in a specific type of logo. So we work with data stewardship to attribute trustworthiness, acquisition date, and other metadata to each data source, so that as soon as they enter the organization, they already have those metadata, which will be very important in case we have data problems or biases. And we also define the main features in terms of AI training. So some of the key features here can include the color or the set of colors of a specific logo, the style, that is, whether it's more like 3D or CG, whether it's drawing or more classical, whether it's metallic, and so on. Or the shapes, for example, whether it has more round shapes or square shapes or any other type of shape, really. So due to lack of resources, what we do here is we run an automated tagger, like Blip, to attribute tags to the existing logos. So maybe we're doing this with a small team, and we can't afford to have people manually reviewing every single logo and attributing the captions to that data point, right? So what we do is we may do a very scarce manual review here and there, but most of the effort is actually automated. Then we have to deal with quality issues. There are certain issues in terms of the data quality that we may find at this stage. So for example, we may find that a lot of our logos are of low resolution. That is, they may be old internal ones from the 90s or even older, and we don't have high resolution alternatives. Maybe because at the time they didn't export the vector file, so we would not be able to re-render the logos in high quality, or maybe because they just weren't saved. But one way or another, we don't have those logos in high resolution, and that counts as a part of the dataset. So we decide to use a generative adversarial network to actually upscale those logos and use the upscaled versions, but we do update the metadata to reflect this, and we may update the captions as well. Because here's the thing, an upscaled logo is not going to have the same quality as that logo in its original resolution if we have it. So we do use some upscaled logos, but we make sure to very explicitly label which ones of these they are. So we fix this issue using this method, if you will. And we appropriately note this down in the metadata, as well as creating an upscale feature to caption these explicitly. So as I just said, right, we actually create a feature called upscaled, so that way, when we have the generative AI model created, we can actually define, do we want to generate a logo that is more like the upscaled ones or not at all? And we also find out that some of our logos have watermarks, and there are no versions without watermarks. And these can be our own watermarks or watermarks from somebody else, from other organizations, in logos that we purchased, for example, or from open source databases. Now, how do we fix this? Well, because we don't have the resources, we decide to simply exclude some of these logos with the watermarks to diminish their impact on the dataset, and we keep others. So, for example, let's assume that there are 20 logos with watermarks in a 400 picture dataset, right? Out of those 20 logos, what we can do is we can use 10 of them and cut the other 10, because that way there's still going to be a little bit of impact in terms of the watermarks on the final data, but it's not going to be that big. And if the logos are good enough, that may be justified to include those watermarks. After we've dealt with the data quality issues, it's now time to deal with biases in the data. So we might start by performing some preliminary form of statistical analysis, and it actually tells us that we have overrepresentation in terms of certain feature values. For example, overrepresentation of certain colors in the color feature. So we do data profiling after that to try and find out what biases may exist. And we find out certain things. For example, we do have overrepresentation of light blue and green logos. And this may be connected to curating a lot of logos from tech companies and from finance companies, especially startups that always have that sort of minimalistic and sophisticated type of logo. So we may have an overrepresentation of those types of logos. And what we do is we cut some of these logos from the dataset to kind of rebalance those feature values in terms of colors and styles, and we decide to actively source more logos with different colors to make the dataset more balanced. And the additional ones that we source may depend on the company, right? Maybe we can ask for more logos from the partners that we are licensing from, or maybe we can just obtain them in an open source manner. Either way, we want to rebalance the dataset. And we may actually also find out that certain styles are overrepresented, namely clean logos made of a simple color contrasted against a white background in a minimalistic style, due to the same reasons, right? Because we have too many tech company logos. So we do exactly the same, right? And what you can notice here is that because we cut some tech logos due to the previous point, this bias is already mitigated a little bit. So what we want to do here is just complement that. We're not going to fight this bias full strength like we did the previous one because they are correlated. So we just make some additional effort to include other logos with color transitions or with gradients in a variety of styles to try and counter the overrepresentation of those minimalistic logos. And then finally, in terms of protecting and securing data, that is in this case, our logo datasets, there are certain elements that we prioritize here. For example, we define strict access control to the logos so that only people that will be working with them have access to varied versions. So for example, the graphic designers and the editors can work with the raw versions of the logos, but there's no reason why anybody else would need to access those files. Then the marketing teams and other business users can access the finalized versions, for example, to include in marketing campaigns or for any other purpose, really. And we also decide to protect our own logos with watermarks to minimize theft and consequences in case of data leaks. This is not a formal security practice that is listed in terms of cybersecurity or logical security, but it is a good practice in this case because we are talking about IP. And we also make sure to use strong physical and logical data controls in both our training data and the outputs of the trained models for security. Basically encryption, locked rooms, security guards, CCTV, the usual practices, good security practices at the end of the day. And now notice, this is not going to be as sensitive as other types of information, right? It almost seems a little bit excessive to say that we're using such strict security controls for logos, as compared to, for example, personal information or sensitive information. But good security practices are always good security practices. So we can keep these logos on encrypted servers or in locked server rooms, basically making sure that we apply the same security controls that we have to data in general to these as well. They're just best practices at the end of the day. So as you see, we follow the usual process with usual steps, mitigating the data quality issues and biases so that we can have a high quality dataset to train our generative AI model. Let's cover a full run-through of training a text generative AI for knowledge-based use. We are going to cover, as usual, curating the data quality issues that may occur, biases that may occur, and the security and privacy piece as well. Let's take a look. Let's talk about this example of creating a generative AI model in terms of text to use in our knowledge base. That is, creating a sort of superpowered chatbot that can answer questions related to anything in our knowledge base. The technology may be something like an LLM like ChatGPT or not, but it's not really relevant to the data because high data quality in this case is always the same. So let's cover this example. So let's say that leadership in our company has decided that we are going to create a generative AI based on the knowledge that is existent in our knowledge base. And this is both to facilitate answering questions for end users, for example, a chatbot for public use, but also to facilitate the redaction of new articles or content in the knowledge base internally. So what we're going to do is we are going to create a public version of the model that is for public questions, and we are also going to have a private version of that model for internal use with more sensitive information. So if the data sources are well classified in terms of metadata, what is sensitive information and what is not, this is actually going to be very easy because we just use one dataset to train one AI and then both datasets to train the sensitive AI. But at the end of the day, the operations are always the same. We have to debias all of the datasets, we have to make sure that there are no data quality issues in all of the datasets, and that we have metadata for all datasets, for example. So the process is exactly the same for both datasets. And as usual, we're going to go through the usual steps that we have in this course, right? We curate or we obtain the data, we make sure that we profile for data quality issues and remedy those issues. We do exactly the same for biases as well, profiling for biases and remediating biases. And finally, ensuring proper data security and data privacy along the way at all stages. So in terms of curating or obtaining the data, all of our data is going to come from one source, which are internal data, right? Because we're talking about our knowledge base, so the only source of information that we have is internal. We may include other things which are not strictly in the knowledge base, such as product manuals, marketing materials, and others that may complement the knowledge base, but at the end of the day, it's all going to be internal. But however, the problem here is that these data have varied levels of sensitivity, right? Because our knowledge base may both contain generic and public information, for example, where to download the software demo or release notes for a specific version, but it may also have highly privileged information that is just for internal use, like sales forecasts, quarterly operational data, legal data, contracts, and a lot more. So we have to be very careful with this. And additionally, these data may depend on the department, right? For example, we may have sensitive information about sales forecasts, which is sensitive and just for sales. And we may have legal information like contracts, which is highly privileged and just for the legal department. So it's not just about whether the data are sensitive or not, but also by whom can they be viewed. But we're going to take care of that in the security and privacy part. So the biggest role of data stewardship here is going to be to help attribute the sensitivity levels to the various types of information. And because these are internal data, this can actually already be done. Or not, it depends on the company. But this helps us prioritize what to protect, and it makes a clear delineation between what is public and what is external. You do not want at all costs for the public chatbot to reveal sensitive information. So naturally, we define the key features which are going to be relevant to train our model, including the sensitivity level, that is, are these data public or private, or how private are they? Or the topics, for example, are they texts related to products, to payment sources, to internal operations, and so on, and also results. That is, in the case of customer issues, were the issues resolved or not? Because we may want texts to train answers in terms of whether you can solve an issue or whether you can't solve an issue, right? What are the best practices for when you can do something to help the customer, but also what are the best practices for when you cannot solve the issue, but you still have to give out a polite and graceful reply. Okay, so all of these are relevant here. So, in terms of data quality issues, we do deal with certain issues. There are always data quality issues, and these include in this case. For example, we have to format all text as a question-answer format if we're training an LLM, for example, and this means that certain texts have lower quality by nature from the get-go because they are not formatted this way. For example, interactions with customers may be very well formatted because they're in the format of one message, then an answer to that message. But for example, if we have product manuals, technical specifications, and others, which may be in a very different format, they're not in that format, and because of that, they have low data quality in terms of training this model from the get-go. So we have to deal with that. And in this case, to be honest, there is nothing that can be done except reformat all of these texts with varying levels of difficulty, right? If there are certain texts which are going to take a lot of processing and we cannot properly do it, we may even not include them in the dataset. Or if we have a very safe version of an existing LLM like ChatGPT, a version that is proprietary and self-hosted and that is secure, we may use it to actually transform the text and put it in this format, always checking for hallucinations and other types of issues as well. Again, a version that is self-hosted and that we own the rights to and that we know is not going to get us in trouble by sharing sensitive information as an option. And we may also have another issue, which is that we may have conflicting information, especially regarding user manuals of different versions. Different texts may simply say different things. For example, maybe in a product manual for a SaaS product, it says that in a specific plan you do not have access to a feature. But maybe we have a customer interaction where a representative actually said that the plan includes that feature. Maybe it was a wrong answer. But we have to resolve resolve these conflicts, because otherwise our model is going to be confused and it's going to give out both types of answers, which we absolutely do not want. In other words, we're pretty much cleaning up the erroneous information before we train with those data. And the major way to fix this is simple, although not necessarily easy, which is to find out the right answer in each case and to cut or correct text from the dataset. That is, we find every single instance where the information is incorrect and we either correct it or we exclude those texts. It's simple in concept, but maybe not that easy to execute, but we still have to do it. And we may also have another problem, which is outdated information in certain documents, right? As in the previous point, we find out which information is useless and we have to cut or correct those texts as well. Maybe there's a version of a manual that says that a feature is in a certain menu, but maybe that feature has changed in a different version of the program. So we do have to find out for the actual version, for the current version, what is the right answer and what is outdated. And again, cut every reference or correct every reference that is not correct. Then, after dealing with the data quality issues, we still have to deal with the biases, as usual. So we may perform preliminary statistical analysis, kind of a mini data profiling. And that analysis may tell us that there is an overrepresentation of sales in the topics. Or in other words, we have a lot of text about sales and we don't have a lot of text about products, marketing, and other parts of our knowledge base. So we follow that up with actual data profiling. And we find out some interesting things. First, we do have an overrepresentation of sales information compared to other types of text. This means that the model would be great at dealing with sales questions if it's trained like this, but it's going to be impoverished for everything else. So what we decide to do is to rebalance the datasets by cutting excessive material that is related to sales and by adding underrepresented topics such as, for example, HR. Maybe we don't have any HR text at all, but we do need that because we want to generate knowledge related to HR with our internal chatbot. So we do have to rebalance those topics so that the model itself is going to be balanced in terms of the outputs. Then, we may also have an overrepresentation of technical text too, and maybe the preliminary statistical analysis did not catch this, but the full data profiling reveals it. Or in other words, we have a lot of jargon in our text, and it's not always directed at users or the general public. Maybe a lot of the text is internal, so there's a lot of jargon and technical vocabulary, but that's not going to do with end users. So what we need to do is to add a new feature, which is called the technical depth, aka the jargon, and ensure that the datasets are balanced according to that as well, right? For example, if it's a very academic type of text, maybe the technical depth is 100 out of 100, depends on the range that we're using, and maybe if we have a marketing material, the technical depth is probably a 10 or a 20. And what we need to do is to ensure that the datasets are balanced in terms of this new feature as well. I mean, if that is relevant to us, it depends on the use case. It may be the use case where we really don't care about the jargon because most of our users are technical to begin with. So all of this makes sense based on your use case, naturally. And finally, as usual, we have to care about protecting and securing data, and we prioritize certain elements such as, first, applying additional security to the most sensitive datasets, both in terms of inputs and outputs. In other words, you should not be protecting your internal operational data with the same level of security controls as your public links to a new version of the software, right? They're completely different things. Or if you protect them all with the same level of security, at least use maximum security for all of these. But you know what I mean. So we have our public dataset to train the public-facing chatbot, and we have our sensitive dataset for internal use, which has much higher security demands, including split key encryption, for example, rigorous access control by role, and possibly a rigorous cataloging of all physical devices containing these data, where they are moved to, where they are repaired, maybe even limiting the places where they can be repaired, and so on. It depends on the sensitivity of the information and the damage that a leak could cause, for example. And also, we may have a situation where our model is going to be updated regularly as we release new versions of the product or as we just have more information, for example, once a month. And this means that we have to keep our datasets permanently, not just once and then discard them, because they are refreshed continuously, and we have to maintain the security controls for those datasets, and also the model outputs, naturally. And we may also apply de-identification techniques to personally identifiable information in the datasets, because we may have personal information in a lot of our internal texts, for example, redacting client names in support tickets or in contracts, or the locations of certain companies, or the dollar values in procurement, or any other type of operational information, right? So we want to redact that personal information for most roles that don't have access to that information. For example, if we are dealing with sales, then that department maybe should have access to the contact information of a customer, but all other departments probably have no use for that information and should not see those fields. So as you see, we deal with certain data quality issues and biases as usual while training this model both for internal use and public-facing use. Let's cover a full run-through of training a discriminative AI to classify fraud in financial transactions. We're going to go through the usual stages as usual, curating and obtaining the datasets, dealing with data quality issues, dealing with biases, and applying security and privacy controls for this specific use case. Let's cover this example of training a discriminative AI for fraudulent transaction classification, a more classical type of example compared to generative AI that is all the rage right now, but still an equally important example. So let's dive in. Maybe we are a small merchant with both an online store and a brick-and-mortar presence, and we are suffering from multiple types of fraud, such as cash return fraud or maybe even identity theft of some customers and so on. So we decide to implement a fraud classification engine to protect ourselves. Fair enough. So we are going to use both internal transaction data as well as data purchased from other merchants or providers that can complement these data. And we are going to go through the usual steps that we covered in the course and that you know so well. First, we curate or we obtain the data, which in this case are these transactions. Then we profile for data quality issues and we remedy them in some way. Then we profile for biases and we remedy those biases as well. And finally, we enforce security and privacy controls along the way. So, in terms of curating or obtaining the data, we are going to use two major datasets. Maybe we have one dataset of internal transactions and another one of purchase transactions from vendors. And this ensures that we cover a variety of fraudulent situations, but we still take into account our own experience, because both are important. And since we are only suffering from cash return fraud in the physical world, maybe we ensure that other fraud types are included as well. Credit card fraud, automated clearinghouse fraud, whatever types of fraud could be possible as well. And data stewardship attributes the usual metadata to these: acquisition date, trustworthiness, and so on. Again, to make sure that if there is a data quality issue or biases, we know where to track them to. And naturally, we also define the main features that we are going to want to train our AI model. For example, fraud, that is whether there is fraud or not in a given transaction, the fraud type, whether it's credit card fraud, cash return fraud, or so on, the amount, that is the actual transaction value paid, the dollar price of the product or set of products of the purchase, then the product categories, because certain categories are more propensive to fraud than others, such as jewelry, consumables like prepaid cards, clothing, gaming, and so on. And also the account age, that is how long ago a person's account has been created. And by the way, we could have other features here, right? I'm giving an example of some important ones, but you could add others which could be relevant, such as the person's location or the average fraud in the area, and so on. So in terms of data quality issues, we do have certain issues. They always pop up. And these include, for example, many transactions are actually missing the transaction value, which is kind of a big deal when the transaction value is crucial, right? So they cannot be integrated into the final data set. They are literally of low data quality according to the completeness dimension. They are incomplete, and on top of that, that feature is a key feature for training, right? So due to data stewardship's diligence, we easily track them to a specific vendor, again, because of the metadata in every specific data set. And maybe we find out that the vendor had an exporting error, so they quickly re-export the dataset and everything is fine again. And maybe we also have some internal transactions that are missing the value as well, maybe because of computer error, and maybe we exclude those. Or maybe we guess what the dollar value was and we attribute those values. As usual, right? When you have values that are missing, either you cut those values and you don't use them, or you try and guess the accurate value for that specific record. And we may also have other issues, which is, for example, certain categories may not be able to be reconciled without huge effort. For example, we may have a consumables category, which includes everything from gift cards to prepaid cards for streaming platforms, gaming, and so on. And we don't have any granularity within that category. So what we want to do is to create subcategories like gaming, streaming, and so on, but we can't because that category is not granular enough. So what we decide to do is to just use the super category for now. And maybe in the future we could have sub-datasets that have these subcategories and train on them. And we may also have certain issues, which is the methods used to classify fraud may be different. Because here's the thing, if we just have a binary field such as, is it fraud, yes or no, this may result from various vendors with varied processes that may be more aggressive or conservative, right? They may use AIs that are propensive towards false negatives or false positives. And if we just have a final Boolean result of fraud, yes or no, then yes, for example, could be 51% probability of fraud that is enough to trigger a yes, or it could be 100%. And we may not have enough granularity, or at least the methods may not be the same. So in the future, we may even move towards a field which is probability of fraud from 0 to 100%. But then we have to migrate all of the other transactions to use this range for this value. Now, we also may have problems related to biases. Again, we run preliminary statistical analysis, and it may tell us that a specific fraud type has overrepresentation, and it's the credit card value in this category. In other words, we have too much credit card fraud compared to other types of fraud, or so it seems from the preliminary analysis. So we decide to actually perform data profiling, and we find out, for example, that certain types of fraud are in fact overrepresented. So we were only worried about cash return fraud being overrepresented, but not only did the partner data make up for this with a lot of credit card fraud, but it actually also overtook it. So now we actually have overrepresentation of credit card fraud because a lot of the data came from vendors and most data is about credit card fraud. So now most transactions are actually of this type. And this may happen in the real world, by the way, right? So we are worried about overrepresentation by feature, and then we integrate a whole new data set, and now there's another feature which is overrepresented, or multiple ones. So what we decide to do is pretty much just to cut some credit card fraudulent transactions from datasets and to ask vendors to re-export the datasets, including other fraud types. So we're doing what we can to kind of rebalance the datasets. And due to the ease of creating synthetic data, we may also do this here. Because if you think about it, it's just numerical and structured data. So it's very easy to just create a record that has a realistic dollar value, a realistic user age in terms of their account, and a realistic product category, and to actually consolidate that as data that can be used. So it's very easy to create synthetic data which are realistic but are not actually from the real world, and we can use that as well to rebalance the data set. And we may also find out that we actually have a geographical and economic bias, and this may be because most of the fraudulent transactions that we have bought are from the US, and this is reflected in associations in terms of IPs or certain locations and specific dollar values for products. That is, in other locations of the world, maybe you don't have the same type of fraud, or products definitely don't have the same dollar value. So we are biased in terms of this. So we may add, for example, continent as a feature and rebalance our datasets. We're not going to go at it by country yet. We're just focusing on what is the continent, what are the usual prices and product categories in the US, in Europe, Asia, and so on. Because at least that hedges against bias in some way. But in the future, sure, we could even go by more granular regions. But at this point, it's just a simple way to hedge against the specific bias. And finally, we can never forget protecting and securing data. And especially in this case, because we're talking about transaction datasets, right? So we have to prioritize having extremely strict physical and logical security to our transaction data, because a lot of the transactions may actually contain the last 4 digits of credit cards. We can redact these to make the data less sensitive, but still we should have very strict security controls. So not only do we apply state-of-the-art physical and logical security to our input datasets, but we may also do the same for model outputs and all associated documentation and model files. If we're dealing with credit cards at the end of the day and we have PCI DSS certification, for example, we probably already have these security controls. We just need to apply them to these data as well. So it's probably nothing new. And then we also have to ensure compliance with the PCI DSS, for example. We may have the case where we already comply because we deal with credit card data, so our existing databases with customer information have to comply, but now we have to update our practices and controls because we have new sources of credit card data. So it's not about starting to comply with the PCI DSS, it's about making sure that we keep complying when our processes are changed and when we have new data sources. And again, a lot of the practices are the above, state-of-the-art security, just applying them to the new sources of data as well. And we also apply extremely strict access control to various roles, because we de-identify the names, the credit card digits, and other personally identifiable information for whichever roles don't need to see them, which are most roles, by the way, and those roles lose access to these data after their work is done. In other words, if you don't have a reason to see the credit card numbers, for example, you should not be accessing them. Or if you don't have a reason to see customer names, you should not be accessing customer names. It's as simple as that, the principle of least privilege in action. So as you see, although the data quality issues and the biases are a little bit different than what we have in the generative AI examples, they still exist and the process is still generally the same. We are now at the conclusion of the 6th module on full run-throughs. Let's take a look at the lessons that we've covered, as well as discuss some key takeaways from this module. Hi, We are now ready to conclude our full run-throughs module about specific examples of everything that we've covered so far. So, in this module, we focused on, for example, specific examples of specific types of AI and with specific data formats, generative for image, generative for text, discriminative AI, and their nuances, or the various problems that can occur at all stages related to data quality, biases, harmonizing datasets, characteristics of the datasets, as well as possible fixes to all of these issues, and in general, just illustrating the various processes that we've covered so far, such as data profiling, remediation, mitigating biases, feature engineering, standardization, and normalization, and others for specific applications. So, what are some of the key takeaways from this module? Well, one is that we may have various priorities when curating the data, including classifying data with their sensitivity levels, gathering data from varied sources to have a balanced dataset, or applying metadata to everything, and defining the main features. By the way, when I say various priorities, I mean that all of these are a priority. Not that some of these are more important than others, right? They may be, but all of these are important, period. Or we may have data quality issues with all aspects of the data, right? We may have missing values. We may have formats that cannot be harmonized. We may have low resolutions in images, different methodologies to classify fraud or to reach any value, conflicting information, missing information, and more. And we always have to correct or exclude those data. Another takeaway is that any feature's values can be biased. We may have an overrepresentation of specific colors, geographies, froth types, or any other feature, right? Or any other feature value in specific. So we must debias and rebalance the datasets. In other words, the values for all features must be correctly distributed. Otherwise, we do have a problem and the model is going to be biased in some way. Unless that is what we want, but in most cases, it definitely isn't. And finally, security and privacy controls are crucial, but they may vary, right? Because we may have stricter security controls for more sensitive information, we may have access control by role based on differing information and differing roles, and we must de-identify personally identifiable information whenever possible to protect the data subjects. And with this, we close the full run-throughs module with specific illustrations of the techniques and topics that we've discussed in this course for specific use cases. To different biases or quality issues. Or, for example, what are the common procedures in terms of curating data, captioning those data, integrating various data sources, profiling data for issues, fixing those issues, and many other operations related to data acquisition or data management for training data. Or the characteristics of high-quality data for AI training purposes, which may vary, right? As well as how to ensure these, how to identify and remediate these issues. Do we know what are the key features for this specific model? Do the records or the data have values for those key features? And are those values evenly distributed, or is there overrepresentation or underrepresentation of some of these, and so on? Or the common biases in datasets, as well as how to identify them and mitigate them, according to the most important features for training. Again, what are the most important features, and are the values evenly distributed? And also the most frequent ways to protect training data in terms of security and privacy controls, but also protecting personally identifiable information. And finally, what are some questions that you can ask to reflect on the content of this course and these practices? Well, do we properly tag our curated datasets with metadata, such as trustworthiness, acquisition date, sampling methods, and methods used to reach certain values, or do we not have those metadata, for example? Or do we formally define the features needed for training? And do we profile for biases and quality issues according to those features? Or do we just hope that the dataset has high quality in general, right? This is very granular work, but also very important one. Or do we formally define the needed feature values as validity rules and standards? That is, does data governance formally define that these are needed? Or do we just accept all data, even if they are of low quality, and then decide to deal with it afterwards? Or what processes do we have to remedy low quality data? That is, how formal are they? And do we draw conclusions from them, right? Is it just something that we do last minute and we ask somebody to take care of it? Or is it a formal process that has a report, conclusions, and we use those conclusions to improve our data governance practices in general? How formal are these? In other words, how sophisticated are we when dealing with data issues? Or do we validate model outputs for bias? And how do we de-bias datasets to train better models, if we even do that, right? So how are bias profiling and remediation done? Again, are they done on a formal level or not at all? Is there feedback between the people who actually use the models and the people who created the models? Very important questions. And by the way, there's no right answer to these questions. They're just supposed to spark reflection in terms of your best practices. What am I missing? What do I already do well? And so on. Or do we know which regulatory frameworks apply to us and how they apply? Are we compliant with, for example, the GDPR, the CCPA, the ECOA, or any other type of regulatory framework that applies to us? Or what are our personally identifiable information practices? Do we tokenize, mask, hash this type of data? Do we even protect these data? And what are our security and privacy controls? And how strict are we with them? That is, how well are we protecting our training data? And with this, we close this course on data governance for AI training data. Thank you so much for your time and congratulations on making it to the end.